Can a broken glass fix itself? Physics says yes. In principle, every molecule could, given enough time, slip back into place. But does it ever happen? Of course not. And that's where things get interesting. You see, the universe is lazy. You are not its hero or its accident. You're just a clever little shortcut it discovered. Every star, every breath, every thought you've ever had is magic. It's the universe figuring out how to get tired faster. We like to think life fights chaos, that we build order, that we struggle against the mess of things. But physics tells a different story. Life doesn't resist entropy. Life accelerates it. The rock just sits there, slowly crumbling. But you eat, move, think, reproduce, rearrange matter at an astonishing pace, all just to stay alive one moment longer. From this point of view, you're not a miracle standing against decay. You're the universe's strategy for decay. It turns out that making stars, galaxies, ecosystems, and thinking beings is the fastest way for the universe to exhaust itself. So the real question isn't why does life exist? It's why does entropy need us so badly? And once you see it that way, everything changes. Suddenly, life, the cosmos, even broken glass, they're all part of the same story. Look at this fresh piece of white chalk. It's long, clean, smooth, one solid piece. I'm holding it up in my hand. This is matter structure, held together by electric forces between atoms. Now I'm going to let it go. I'm going to drop it straight onto the hard floor. There it goes. You just heard it hit the floor. What was one solid piece is now several broken pieces in a little cloud of white dust scattered on the ground. It broke. I'm not picking it up, and I'm leaving it exactly where it landed. Now suppose I wait here. Suppose we all wait here. We have patience. We wait 5 minutes. We wait a year. We wait 10 million years. Is anything going to happen? Is the floor going to suddenly shake just right and send a kick of energy into that white dust? Is heat going to rush out of the air, cooling the room, and use that energy to fuse the calcium carbonate back together? Will the chalk lift itself off the floor, fly up into the air, and land perfectly back in my hand, whole and smooth? You laugh because you know it won't happen. You know that if you wait for the age of the universe, that chalk is never coming back to my hand. It is irreversible. But here's the question, and it is a deep mystery, maybe the deepest of all. Why? Let's look at this equation, F equals ma. Newton, the laws of motion. If I push an atom, it moves. If I push it the other way, it moves back. Now I'm writing another set of equations next to it. These are Maxwell's equations, and now one more. This is the Schrödinger equation. These equations, these are the rules of the game. They are the laws that tell the atoms what to do. And here's the thing. I want you to pay attention to one symbol in these equations, the letter T. That's time. If I take T and replace it with minus T, if I reverse the direction of time in the mathematics, the equations still work. They don't care. If I make a movie of the planets going around the sun and play it backwards, does it look wrong? No, the physics is perfect. If I show you two atoms colliding, bam, and bouncing apart, and then I run that film backward, the atoms come back together, collide, and bounce away again. You cannot tell the difference. At the fundamental level, nature does not seem to know the difference between past and future. But this thing knows the difference. If I showed you a movie of this chalk jumping off the floor into my hand, you would say, Professor, that's a fake. You're running the film backward. So now we have a paradox. The atoms inside the chalk follow laws that work both ways in time. But the chalk itself, the collection of atoms, only goes one way. Things break, people get old, smoke spreads out, it does not rush back into the cigarette. We remember yesterday, we do not remember tomorrow. We call this the arrow of time. And for a long time, it drove physicists crazy. Because the arrow is not in the laws of motion, it's not in quantum mechanics. So where does it come from? Here's the answer. It isn't in the atoms themselves, it's in the counting. Imagine the air in this room. You can't see it, but all the molecules are bouncing around constantly. Right now, they're spread out evenly. But is it possible? Is it allowed by the laws of physics for all the air molecules to suddenly move into one corner of the room, leaving the rest of us to suffocate? Yes, it is allowed. Newton doesn't forbid it. Quantum mechanics doesn't forbid it. There is no law of physics that says the air can't all move into one corner. So why doesn't it happen? Because there are very few ways for the air molecules to all be packed into one corner. But there are trillions upon trillions upon trillions of ways for the air to be spread out across the entire room. Nature isn't choosing. Nature isn't forcing anything. The universe is just shaking the box. And because there are overwhelmingly more disordered arrangements than ordered ones, that's where the system ends up. We call this entropy. Entropy is a measure of how many different ways the inside of something can be arranged without changing how it looks from the outside. But wait, this leads to something strange, something that should bother you. If entropy always increases, if things always get more mixed up, more broken, more disordered, that means yesterday the universe was a little more organized than today, and the day before that, even more organized. If you follow that logic all the way backward through the history of the Earth, back past the dinosaurs, back past the formation of the stars, you reach a staggering conclusion at the very beginning, at the Big Bang. The universe must have started in a state of unbelievably low entropy. It was wound up tight like a clock. Everything that happens now, the chalk breaking, the sun shining, you breathing, your heart beating, all of it is just the slow unwinding of that initial spring. So why does the chalk break? Because the universe started smooth. And why are you alive? Because the universe wants to get messy. And you're a very clever machine for making a mess. So now, let's talk about how that works. Let's talk about the great unraveling. So we have a problem. The atoms don't care about time, but the chalk does. The atoms can go backward, but the chalk only breaks forward. To understand this, to really get to the bottom of it, we have to stop thinking like philosophers and start thinking like accountants. We have to learn how to count. Now, I want you to imagine a box. Let's make it a sandbox, like you played in when you were a kid, divided right down the middle with a little cardboard wall. On the left side, we fill it with black sand, pure black. On the right side, we fill it with white sand, pure white. This is a very special arrangement. It is orderly. It is separated. We can look at it and say left is black, right is white. It has structure. Now I lift up the cardboard wall. Nothing happened yet. The sand just sits there. But now I give the box a shake, just a little shake. What happens? The grains near the middle start to bump into each other. A few black grains hop over to the right. A few white grains hop over to the left. The line gets blurry. I shake it again, a bit harder, more mixing. The gray zone in the middle gets wider. I keep shaking, shake, shake, shake. Eventually, what do I have? I have a box of gray sand. It's all mixed up. Uniform, boring. Now here's the question that determines the fate of the universe. If I keep shaking the box, if I sit here and shake it for 1,000 years, will the sand ever accidentally separate back out? Will the black grains suddenly all agree to go left and the white grains all agree to go right? Your intuition says no. Your common sense says, Professor, don't be ridiculous. But remember, we are physicists. We don't trust common sense. We trust the laws. And the laws of motion say that if I bump a grain of sand, it moves. It doesn't know what color it is. It's just bouncing. So is it physically impossible for the shaking to push all the white grains right and all the black grains left? No, it is not impossible. There is no law against it. If you bump the box exactly the right way, applied exactly the right forces to exactly the right grains, they would separate. So why doesn't it happen? It's not physics, it's mathematics. It's the art of counting. Let's look closer. Let's become microscopic. Suppose I look at the box when it's all gray. I take 2 grains of sand, one black, one white, that are right next to each other in the middle of the pile, and I switch them. I swap their places. Does the box look any different to you? No, it's still gray. I take 1,000 grains on the left and swap them with 1,000 grains on the right. Does it look different? No, it's still just a gray mess. You see, there are trillions of ways to arrange the grains so that the box looks gray. Trillions upon trillions of different internal arrangements, what we call micro-states, that all result in the same outside appearance, the macro state of being mixed. But now, Think about the start. Think about the separated box, black left, white right. If I take a black grain from the left and swap it with a white grain from the right, does the box look different? Yes. Now there is a speck of white in the black. It is no longer perfectly separated. There is only one way to be perfectly separated. One. But there are 10 to the power of 23 ways to be mixed up. So when I shake the box, I am not directing the sand. I am not forcing it to be gray. I am simply moving the system from one arrangement to another blindly. I am sampling the possibilities. If there is only one arrangement that looks ordered, and a billion trillion arrangements that look disordered, and I am blindly jumping around, where am I going to end up? I am going to end up in the gray. Not because nature prefers gray. Nature doesn't care. Nature is indifferent. Nature is just wandering through the possibilities. It is overwhelmingly more probable that we end up in a state with many, many arrangements than a state with only one. This brings us to a very famous word, a word that people use to sound smart at cocktail parties, but often they don't know what it really means. Entropy. People say entropy is disorder. Well, that's a little vague. Disorder is a human word. My desk is disordered, but I know where everything is. Let's be precise. Entropy is a measure of the number of microstates. It is a count of how many ways you can rearrange the insides of a thing without changing its outside appearance. The box of separated sand, low entropy. Why? Because there are very few ways to arrange the grains and keep it looking separated. The box of gray sand, high entropy, extremely high, because there are practically infinite ways to arrange the grains and keep it looking gray. So when we say entropy always increases, or the second law of thermodynamics, we aren't talking about a force. It's not like gravity pulling things down. It's not like electricity pushing things apart. The second law is a law of probability. It says things tend to go from states with few possibilities to states with many possibilities. That's it. That is the secret of the universe. The chalk breaks because there is only one way to be a solid stick of chalk, but there are infinite ways to be a pile of rubble on the floor. The heat flows from your hot coffee into the cold air because there are more ways for the energy to be spread out than for it to be concentrated in the cup. Now, you might ask, and you should ask if you're awake, but Professor, isn't it possible, even if it's unlikely, that the sand separates? Yes, it is. If we had a very tiny box, a box with only 4 grains of sand, 2 black, 2 white, if I shake that tiny box pretty often, maybe once every fight you shake, I'll get the 2 blacks on the left and the 2 whites on the right. In a microscopic system, violations of the second law happen all the time. Things get ordered by accident. But the universe is made of 4 particles. It's made of uncountable numbers of particles. When you deal with large numbers, Avogadro's number, billions of billions, the unlikely becomes the never. If I sit and shake that real sandbox, the probability of it separating by accident is so small that if I shook it 1 billion times a second for the entire age of the universe, it would never happen. Not once. We are trapped by the numbers. We are drowning in probability. This is what Boltzmann realized in the 1800s. He was a tragic figure, Ludwig Boltzmann. He saw this truth, that the solidity of the world, the irreversibility of time, was just a statistical accident of large numbers. His critics hated it. They wanted absolute laws, not gambling laws, but Boltzmann was right. The arrow of time that we feel, the reason we can't go back to the past, is simply because there are so many more places to go in the future. The future is the land of high entropy. The future is the gray sand. But wait a minute. This leads us to a precipice, a cliff. If entropy is always increasing, if the universe is always getting messier, always sliding toward the gray, that tells us something about the past. It means yesterday the entropy was lower, and last year it was lower still. And if we go back and back and back and all the way to the beginning, it implies that the universe began in a state of absolutely staggering order, a state of impossibly low entropy. Why? Why did the universe start with the sand separated? Who set up the box? Because if the universe had started normally in a high entropy mess like a black hole or a hot soup, nothing would ever happen. We would already be in the gray. There would be no stars, no burning, no life, no time. Time only flows because the universe is unwinding from a very tight knot. So the mystery shifts. The question isn't why does the chalk break? The answer to that is easy. Probability. The real question is why was the chalk whole in the first place? To answer that, we have to look at the biggest system of all, the cosmos itself, and we have to ask about the Big Bang. Because contrary to what you might think, the Big Bang wasn't just a loud explosion. It was the most precise, ordered, low-entropy event that has ever occurred. Let me explain what I mean by that. So we have established the rules of the game. We've established that nature is a gambler, and she always bets on the outcome with the most possibilities. The law of large numbers tells us that the chalk breaks, the coffee cools, and the air mixes, simply because there are more ways to be messy than to be tidy. We call this the arrow of time. It points from order to disorder, from low entropy to high entropy. But now, I want you to stop. I want you to take that logic, that simple statistical logic, and I want you to drive it in reverse. I want you to look backward. If entropy is always increasing today, that means yesterday the entropy was lower. The universe was a little bit tidier yesterday, and the day before that, tidier still. And if you keep going back through the centuries, back through the rise and fall of civilizations, back through the ice ages, back to the dinosaurs, the universe must have been getting more and more organized, more and more structured. If you follow this road all the way to the end, or I should say to the beginning, you arrive at a moment 13.8 billion years ago, the Big Bang, and here's where we walk into a trap, a logic trap that confuses even the best students. You see, when you watch a documentary on TV, they show you the Big Bang. And what do they show? Big boom, a giant explosion, fire, chaos, debris flying everywhere. And you think to yourself, well, surely an explosion is high entropy. Surely an explosion is messy. But if the Big Bang was high entropy, if it was already a mess, then the universe would have been dead on arrival. There would be no place for the entropy to go. There would be no hill to roll down. If the universe started in a mess, and nature loves a mess, it would just stay a mess. No stars would form, no galaxies, no life, just a hot soup forever. So the Big Bang could not have been a messy explosion. It must have been, paradoxically, the most organized, precise, low-entropy state imaginable. Now, you're going to ask me, but Professor, the early universe was a hot gas. It was a soup of particles. In the sandbox example, you told us that mixed-up gas is high entropy. Aha! You are paying attention. But you are missing one player. You are missing the joker in the deck, gravity. Gravity changes the rules of entropy completely. In a box on a table where gravity doesn't matter much, smooth means high entropy. But the gas spreads out. That's the end of the story. But in the universe, where gravity is the boss, gravity wants to pull things together. Gravity wants to clump. Gravity wants to crush. So if you have a universe filled with gas and you let gravity do what it wants to do, what is the high entropy state? What is the final, messiest, most probable state? It's not a smooth gas, it's a black hole. A universe filled with black holes, everything crushed into dense, dark points, and that is the gray sand of gravity. That is the maximum disorder. So look at the Big Bang again. Was it a bunch of black holes? No. We look at the cosmic microwave background radiation, the baby picture of the universe, and what do we see? It is smooth, shockingly smooth. The density of the gas on one side of the universe is the same as the density on the other side, to within 1 part in 100,000. It is uniform. It is flat. It is unclumped. Do you realize what this means? In a world governed by gravity, smooth is not the end. Smooth is the beginning. A smooth, uniform gas is a state of tremendous tension. It is like a weight lifted high in the air, waiting to drop. It is a state of incredibly low entropy. The universe started with the gas perfectly spread out, defying the pull of gravity, holding its breath. This is the past hypothesis. The hypothesis that for some reason the universe began in a specific, rare, highly ordered state. Now, how rare, how lucky was this? We can calculate it, and the result is a number so big it makes me sweat just thinking about it. My colleague, Roger Penrose, a brilliant man. He thinks about geometry in ways that would make Euclid dizzy. He sat down to calculate the probability. He asked, out of all the possible ways you could arrange the matter and energy of the early universe, how many of them looked like our smooth Big Bang, and how many of them looked like a messy universe full of black holes? He came up with a number. The odds of our universe happening by accident are 1 in 10 to the power of 10 to the power of 123. I want you to look at that number. That is a double exponent. It's not 10 to the power of 123. That's a small number. That's just a 1 with 123 zeros. I could write that on the blackboard. This is 10 to the power of 10 to the power of 123. If I tried to write this number out, if I wrote a 0 on every proton and every neutron and every star in every galaxy in the visible universe, I would run out of particles before I even finished writing the exponents. It is a number so large that there are no names for it. It represents a precision that is essentially infinite. It tells us that the creator, or whatever mechanism started this whole show, didn't just throw the dice. It's as if the creator had a pin, and there was a map of all possible universes. A map larger than the galaxy. And most of the map, 99.9999% of it, is marked black holes and chaos. And there is one tiny microscopic dot smaller than an atom marked smooth, life-supporting universe. And the creator took that pin and stuck it exactly on that dot. Why? Why did the universe start in such an unlikely state of order? Standard physics doesn't tell us. The Big Bang Theory describes what happened after the bang. It tells us how the fire expanded, but it doesn't tell us why the wood was stacked so neatly in the fireplace to begin with. This is the mystery of the low entropy past. And understand this. This mystery is the battery that powers your life. The only reason the sun shines today is because the gas in the early universe was smooth and separated, and gravity has been slowly pulling it together for 14 billion years, heating it up, creating stars. The only reason you can digest your lunch is because the sun shines. The only reason you can form a memory, the only reason you can remember the sentence I just said, is because your brain is increasing the entropy of the universe, riding the wave of that initial order. We are all just surfing on the wake of the Big Bang. But think about the alternative. Boltzmann, the father of entropy, he struggled with this. He thought that maybe the universe is mostly a mess. Maybe we are just a fluctuation. You know, if you wait long enough in a chaotic box of gas, eventually a few atoms will bump together and form a brain. Just a brain, floating in the void. A Boltzmann, a machine, and that brain might think, I exist, I see a universe, and then poof, it dissolves back into the chaos. Statistically, it is vastly more likely for a single brain to pop into existence out of the chaos than for an entire smooth, orderly universe to be created. So why aren't we Boltzmann brains? Why do we see a huge, consistent universe with billions of galaxies in history and fossil? Because something special happened at the start. So the next time you drop a piece of chalk, when it hits the ground and snaps, that snap is an echo of the Big Bang. The chalk breaks because 14 billion years ago, the universe was wound up tight, like a clock. And for 14 billion years, the spring has been uncoiling, creating galaxies, creating planets, creating us. We are the ticking of that clock. We are the relaxation of that initial tension. But here is the cliffhanger. Here is the question that keeps physicists up at night staring at the ceiling. We know the clock is unwinding. We know that's why time froze. But who wound the clock? What mechanism before the Big Bang set the entropy so low? Was it a cycle? Was it a bounce? Was it something we haven't even invented the mathematics for yet? We don't know. But to find out, we have to look at the one place where entropy, gravity, and quantum mechanics all crash into each other. We have to look at the trash cans of the universe. We have to talk about information. And we have to talk about the demon. Now, I want to tell you a story about a little guy who tried to beat the system. We said before that nature slides toward disorder. We said the chalk breaks and doesn't come back together because there are more ways to be broken than to be whole. We said it's just probability, the law of large numbers. But is it just numbers, or is there a way to cheat? In 1867, James Clerk Maxwell, the same genius who gave us the laws of light, came up with a puzzle that bothered physicists for 100 years. He invented a demon, Maxwell's demon. Imagine our box of gas again, but this time let's put a wall right in the middle, dividing it into two chambers, A and B. The gas is all mixed up. Some molecules are fast, hot. Some are slow, cold. They are averaging out to a boring, lukewarm temperature, maximum entropy. But in the wall, there is a tiny little door, and operating that door is a tiny little creature, our demon. He's very small, and he's very quick. He watches the molecules coming toward the door. He sees a fast molecule coming from the left. He thinks, aha, that's a hot one. He opens the door, zip, lets it through to the right side and shuts the door. Then he sees a slow molecule coming from the right. He thinks, you go to the left. Open, zip, shut. He does this for a while. He's sorting them. He's acting like a traffic cop. He is letting all the hot stuff go to the right and all the cold stuff go to the left. Now stop and look at what he has done without doing any heavy lifting, just by opening and shutting a frictionless little door. He has separated the gas. One side is boiling hot. The other is freezing cold. He has created order from disorder. He has lowered the entropy of the box. If you could do this, you could build a machine that takes heat from the air and turns it into power forever. You could drive a ship across the ocean by sucking the heat out of the seawater and leaving ice blocks behind. You would have a perpetual motion machine of the second kind. So the question is, why can't we build the demon? Is it just that we don't have tiny enough tweezers? Is it an engineering problem? For a long time, people thought maybe the door is heavy, or maybe the demon gets tired. But that's not it. We can imagine a robot demon with a frictionless door. The answer came much later, and it links thermodynamics to something you might not expect: information. Think about what the demon actually has to do. He can't just open the door randomly. If he does that, the gas just mixes. To sort them, he has to know which molecules are fast and which are slow. He has to look. He has to measure. He has to take a snapshot when he sees a molecule. His brain or his microchip goes from a state of I don't know to a state of fast. He has gained information. Now, gaining information, measuring, surprisingly, you can do that with very little energy. That's not the problem. The problem is the notebook. The demon has a finite brain. He has a finite memory. After he sorts 1 billion molecules, his memory is full. He has written down fast, slow, fast, fast, slow. The hard drive is full. To keep working, to keep sorting, he has to clear his memory. He has to erase the old data to make room for the new data. And here is the beautiful, terrible catch. This is called Landauer's principle, named after Rolf Landauer at IBM. He discovered that erasing information is a physical act. You cannot destroy information without a cost. When you wipe a bit of memory, when you reset a 1 back to a 0, you must dump heat into the environment. It is inescapable. The laws of physics say that to forget, you must radiate heat. So let's look at the demon again. He sorts the gas. He lowers the entropy of the box. The gas gets organized. But to do it, he fills his brain with data. Then to continue, he has to scrub his brain. When he scrubs his brain, he releases heat. How much heat? It turns out the amount of heat he releases into the room increases the entropy of the room by exactly the same amount or more. Then he lowered the entropy of the gas. He didn't beat the second law. He just moved the mess from the box into his own head and then breathed it out as heat. The demon is sweating entropy. This is a profound realization. It tells us that information is physical. It's not just abstract numbers. A bit, a 0 or a 1 isn't just an idea. It is a physical thing that requires energy to manipulate. This changes how we see the universe. Entropy isn't just disorder like a messy bedroom. Entropy is hidden information. Think of it this way. If I have a deck of cards and I know exactly the order, ace of spades, 2 of spades, etc., to me, the entropy is 0. I know everything. If I shuffle the deck and put it face down, the entropy is high. But did the cards change? No. What changed? My knowledge changed. Entropy is a measure of what we don't know about the microstates, is the gap between the macroscopic view, the pile of cards, and the microscopic reality, the specific order. Now, if entropy is information, and information is physical, what happens when you throw information into the ultimate trash can? What happens when you throw a book into a black hole? Let's get weird. According to Einstein, a black hole is a region where gravity is so strong nothing can escape, not even light. If you fall in, you're gone. Classically, a black hole is very simple. It has mass, it has spin, it has charge. That's it. John Wheeler said, black holes have no hair. They are smooth. So imagine I take the Encyclopedia Britannica. It is full of information, millions of bits of ordered data, low entropy. I throw it into a black hole. Gulp. It's gone. The black hole gets a little heavier. But since the black hole is smooth and featureless, it looks like the information has vanished from the universe. If the information vanished, then the entropy vanished. I took order and I deleted it. I lowered the entropy of the universe. I broke the second law. This kept Stephen Hawking awake at night. It kept Jacob Bekenstein awake. They argued about it. Bekenstein said, no, the black hole must have entropy. If I drop a hot cup of tea into a black hole, the entropy of the universe must go up. The black hole must swallow the entropy and keep it. But if a black hole has entropy, it must have a temperature. And if it has a temperature, it must radiate heat. And Hawking said, don't be silly. Black holes don't radiate. They are black. But then Hawking did the math. He did the calculation using quantum mechanics near the edge of the hole, and he found something that shocked him. He found that Bekenstein was right. Black holes are not truly black. They glow. They radiate heat, what we now call Hawking radiation. But here is the most fascinating part, the part that connects everything we've talked about today. When you throw the encyclopedia into the black hole, where does the information go? We used to think it was crushed into the center, the singularity, but the math suggests something else. It suggests that the information about the book, the arrangement of its atoms, the words on the pages gets smeared out. It gets plastered onto the surface of the black hole. The event horizon, the horizon is like a shell, and the information is stored there like a mosaic. And when they calculated how much information a black hole can hold, they found a formula. The Bekenstein-Hawking entropy equals Kc cubed A divided by 4gh bar. You don't need to memorize the constants. Look at the A area. Usually, if I want to know how much stuff I can pack into a box, I ask about the volume, the inside. But for a black hole, the object with the maximum possible entropy in the universe, the amount of information it holds depends on its surface area, not its volume. It's like the universe is a soup can. The soup is inside, but the label, the description of the soup is written on the outside. This has led to a crazy idea called the holographic principle. It suggests that maybe the three-dimensional world we see, the room, the stars, you, me, is a projection, a hologram. That the real information is stored on a two-dimensional surface at the edge of the universe, and we are just the projection of that data into three-dimensional space. Why? Because gravity and thermodynamics are telling us that the deep reality is about information storage. We started with a cup breaking on the floor. We asked, why? We found it's because of counting. We found that counting leads to entropy. We found that entropy is information, and we found that information is what structures space and time itself right at the edge of a black hole. So the arrow of time, the reason you can't remember the future is because the universe is writing a book that is getting longer and longer, and you can't read the pages that haven't been written yet. But what drives the writing? What is the ink that brings us to the most complex machine in the universe? A machine that eats entropy for breakfast. Let's talk about life. So we have looked at the beginning of the universe, the winding of the clock, and we have looked at the end, the gray sand, the black hole, the heat death. But something is bothering you. I can see it. You are sitting there looking at me, and you are thinking, But Professor, look at us. If the whole universe is running down, if the inexorable rule of nature is that things get messy, that things break, that information washes away, how do we exist? Look at your hand. Look at the complexity of your eye. Look at the person sitting next to you. You are not a mess. You are a marvel of organization. You have DNA wrapped up in chromosomes. You have proteins that know exactly how to fold. You have a heart that beats in a perfect rhythm. You have a brain that can think about calculus. If I take a pile of atoms and leave them alone for 1 billion years, the second law says they should just drift apart into gas. They shouldn't accidentally assemble themselves into a mitochondria or a nervous system. So are we breaking the law? Is life a miracle that stands outside of physics? For a long time, people thought so. They thought there was a vital force, an élan vital, that pushed back against the chaos. But in 1944, a physicist, Erwin Schrödinger, the same guy with the cat, wrote a little book called What is Life? And he saw the answer. He said, life is not a closed system. You see, the second law, the rule that entropy always increases, only applies strictly to the whole box, the whole universe. But you are not the whole box. You are an open window. Schrödinger realized that we stay organized, we stay complex, and we stay young, at least for a while, by creating a massive amount of mess somewhere else. We are entropy eaters. Now, be careful here. This is where language tricks us. You say, I'm hungry, I need to eat to get energy. That is scientifically wrong. You do not eat energy. The first law of thermodynamics says energy is conserved. It cannot be created or destroyed. Think about it. You eat a potato. That potato has chemical energy. You digest it. You walk around. You generate body heat. You radiate that heat into the room. If I measured the energy of the potato, and then I measured the heat you gave off plus the work you did, they are exactly the same. You didn't use up the energy. You just moved it through you. So if the energy count is the same coming in and going out, what did you keep? What did you gain? You gained order. You gained negative entropy. Let's look at the ultimate source, the sun. This is the most beautiful engine in the solar system. The sun sends us light, but not just any light. It sends us photons that are very hot. Yellow light, visible light. These are high energy, high frequency photons. They come in a nice direct beam, very organized, low entropy. The earth and the plants on it catches one of these high quality yellow photons. The plant uses that photon to do a very difficult magic trick. It takes carbon dioxide and water, which are lazy, stable, messy molecules, and snaps them together into sugar. It builds structure. It builds a leaf. Now the energy has to go somewhere. The Earth isn't heating up forever, so the Earth radiates heat back out into the dark of space. But here's the catch. The Earth is much cooler than the sun, so it doesn't send back yellow light. It sends back infrared light, heat radiation. To balance the energy equation, for every one yellow photon the Earth absorbs, it has to send back roughly 20 infrared photons. Do you see the accounting trick? Input, 1 photon, 1 piece of data. Output, 20 photon, 20 pieces of data. We took a state with few possibilities, 1 photon coming in, and turned it into a state with many possibilities, 20 photons scattering out in all directions. We increased the disorder of the universe. We took a nice, neat beam of energy, chewed it up, and spit it out as a chaotic spray of heat. And in exchange for doing that, in exchange for degrading the quality of the universe's energy, we get to keep a tiny little bit of order for ourselves. We pay for our life by polluting the cosmos with entropy. This is what metabolism is. It isn't just burning fuel. It is a process of taking in low entropy structure, food, oxygen, stripping out the order to repair our cells, and excreting high entropy waste, heat, carbon dioxide, our sweat. We are mechanisms for degrading energy. Now this brings us to the cutting edge, the stuff that is happening right now in biophysics. People used to think that life was struggling against the universe, that we were swimming upstream, but there is a new idea, a strange idea. What if nature likes us? Not because nature is nice, but because nature wants to reach the gray sand. Nature wants to reach equilibrium. Nature wants to mix the paint. If you have a pool of oil and a pool of water, they mix slowly. But if you put a little whisk in there and stir it, they mix fast. Maybe, just maybe, life is the whisk. Think about a rock sitting in the sun. It gets hot. It radiates heat. It's okay at increasing entropy. But a tree grabs the sunlight, turns it into chemical energy, drops leaves. The leaves rot. Bacteria eat them. The heat is released. A forest is much, much better at taking high-quality energy and smashing it down into low-quality heat than a desert is. And a human city, with our cars and our lights and our computers, we are burning through the Earth's resources, turning organized coal and oil into chaotic heat and smoke at a rate that is unbelievable. From the perspective of thermodynamics, we are the champions. We are the most efficient chaos makers the universe has ever seen. So you are not an accident. You are not a violation of the law. You might be the inevitable result of a universe that is trying to cool down. The universe wants to increase entropy. It found that empty space is too slow. It found that rocks are too slow, so matter self-organized. It built complex little machines, bacteria, plants, you, that are incredibly good at hunting down pockets of water like a cheeseburger or a lump of coal and dissolving them. We are the catalysts of the fall. We are like the little whirlpools that form when water drains out of a bathtub. You know those whirlpools, they look like structures. They have shape, they spin, they look stable. But why are they there? They are there to help the water go down the drain faster. We are the whirlpools. We look permanent. We look structured, but we are just the shape the water takes as it rushes down the drain of the universe. Does that make you feel small, or does it make you feel connected? Because it means we are part of the flow. We are the process. We are the wave, not the water. And just like the whirlpool needs the flow of water to sustain its shape, we need the flow of energy to sustain ours. The moment the flow stops, the moment you stop eating order and excreting chaos, the structure collapses, the whirlpool vanishes, and you become part of the gray sand. That is death. Death is simply the moment when you stop exporting entropy and succumb to it. But until then, as long as the sun shines and the plants grow, we can keep the dance going. We can borrow a little bit of order from the sky, hold it in our hands for a few decades, build a memory, love a person, figure out a law of physics, and then pay it back to the dark. It's a fair trade, don't you think? Now, before we finish, I have to address something. I have to address the feeling in the room, because when you really understand what I've told you today, and when you really grasp the second law, some people find it terribly depressing. They come up to me after class and they have these long faces. They say, "Professor Feynman, you're telling me the universe is dying? You're telling me that everything we do, building cities, writing symphonies, having children, is just a temporary accident? That eventually the stars will burn out, the black holes will evaporate, and the whole thing will end in a dark, cold, boring soup of nothingness. They call it the heat death, the big freeze, and they say, what's the point?" And I look at them and I say, but look at the view. Think about it. If the universe wasn't dying, if the universe was already perfect, if the entropy was already maximized, nothing would happen. A universe in equilibrium is a dead universe. It is static. It is timeless. There is no flow of energy. There's no light. There is no thought. The only reason anything happens at all, the reason the sun shines, the reason the wind blows, the reason your heart pumps blood, the reason you can sit there and wonder about these things is because the universe is moving towards disorder. We are living in the transition. We are the sparks flying off the grinding wheel. Imagine a ball rolling down a very long, very bumpy staircase. At the top, high energy, order. At the bottom, it stops. Silence. But we are the tumbling. We are the dance of the universe falling down the stairs. And what a magnificent dance it is. It's a complicated, intricate, beautiful stumbling that we call history and evolution and life. We are the beneficiaries of the flow. We are riding the wave of the arrow of time. So when you leave here today, when you go out into the world, look at the decay. Look at the rust on an old car. Look at the leaves rotting on the ground. Look at the steam rising off your coffee and disappearing into the air. Don't be sad. Don't say, oh, look at that. It's all falling apart. Say, aha, I am witnessing the engine of reality. And when you see a cup smash or a piece of chalk break, don't regret it. It's just the universe exploring another possibility. It's the arrow of time passing right through your kitchen. The atoms are still there. The energy is still there. It's just that the information has changed. The story has moved forward. Isn't it a wonderful thing? Isn't it a miracle of probability? That out of all the trillions of ways the universe could be arranged, out of all the gray sand and empty space, and for this brief, shining moment, the atoms arrange themselves into us. We are here, we are awake, and we have just enough time to look around and see how beautiful the falling is. Thank you. If I removed every atom from the universe, something would still be left behind, and that nothing is actually doing all the work. You're not made of particles. You're made of quantum fields or simply fields. So what is a quantum field? And why does modern physics depend on it? To answer that, we need to talk about nothing. Because in physics, nothing isn't empty. I want you to imagine a box, a simple shoebox. And we are going to do something very difficult today. We are going to try to understand what is inside it when there is nothing inside it. Now we are going to perform an experiment. In your mind, I want you to help me empty this box. We take out the shoes, obviously. We shake out the dust. We get a vacuum pump, the best one made in Pasadena, and we pump out the air, every last molecule of nitrogen, oxygen, argon. We get it all out, but we are not done. Light is still going through the box. Photons are bouncing off the walls. So we shield it. We wrap it in lead, thick lead. No light gets in. But wait, the walls of the box are warm. The atoms in the cardboard are shaking, radiating heat, infrared waves into the inside. So we have to cool it down. We freeze this box down to absolute zero. 0 Kelvin. The atoms in the walls stop shaking. They are perfectly still. So now we have removed the matter, we have removed the light, we have removed the heat. What do we have left? What's left? Nothing. Empty space. A void. No. That is the great mistake of intuition. You think it's empty because you can't see anything with your eyes. But if we look close enough, if we had a pair of quantum glasses, we would see that this box is not empty at all. It is a boiling, bubbling soup. It is alive. This nothing, this vacuum, is perhaps the most complicated thing in the universe. And to understand why, we have to look at the rules of the game. The rules of quantum mechanics are more. You remember Heisenberg, Werner Heisenberg. He gave us a headache called the uncertainty principle. Now, usually we write it like this. Delta x times delta p is greater than or equal to h bar over 2. You know this. You can't know the position and the momentum of a particle at the same time. If you catch the electron and pin it down so you know exactly where it is, its momentum goes crazy. It wiggles away. Nature refuses to be pinned down. But here's the trick. This doesn't just apply to particles. It applies to fields. It applies to nothing. Imagine the electric field inside that box. Suppose you say, Feynman, the box is empty, so the electric field is 0 everywhere. Well, if the field is 0, we know its value. 0, that's like knowing the position. And if it stays 0, we know its rate of change is also 0. That's like knowing the momentum. We would know the value of the field and its rate of change perfectly. We would know everything. And Heisenberg says, he's wrong. Illegal. Nature forbids total silence. Nature says, I need a little wiggle room. So even in the dark, even at absolute 0, the electromagnetic field cannot sit still. It must fluctuate. It jiggles. It oscillates. The value of the field creates a little hill, then a valley, so up and down incredibly fast. We call this the 0-point energy. Think of it like a pendulum. In the old physics, classical physics, if you take the energy out of a pendulum, it hangs straight down and stops, dead still. Position is bottom, velocity is 0, minimal energy is 0. But in quantum mechanics, that ball is never truly still. If it were perfectly still at the bottom, we'd know its position and momentum perfectly. So it quivers, it has a jitter, it has a minimum energy, half a quantum of energy, that you can never, ever take away. Now go back to our box. This box is not empty space, it is packed with an infinite number of these pendulums. Every point in space, every single point is a harmonic oscillator, and every one of them is quivering with a zero-point energy. Particles, electrons, photons, they are not just little marbles flying through an empty void. No, they are excitations of this jittering medium. When we create a particle, we're just giving one of these sleeping pendulums a big kick. We are adding energy to the soup. So you see, empty space is not a stage. It is not a passive floor where the actors walk. Space is the actor. The vacuum is a medium, brimming with potential, seething with activity. You might ask, Professor, if there is so much energy in this empty box, why don't I explode? That is a very good question, a very dangerous question. Because if you do the math, if you add up all the jitters of all the oscillators in this tiny box, the answer you get is not just big, it's infinite. Or if we are being clever with modern cosmology, it's about 10 to the power of 120 times bigger than what we see in the expansion of the universe. That is the worst prediction in the history of science. We missed by 120 zeros, but clearly we are still here. The box doesn't explode, so how does nature handle this infinite energy? How do we tame the infinite mattress? That, my friends, is where the real fun begins. All right, so we have this jiggling mattress of a vacuum. That's the stage. But now we have to talk about the actors. We have to talk about particles, electrons, protons, photons, and we have to talk about a very embarrassing problem that we physicists had for about 20 years. You see, we had a revolution. We had quantum mechanics. And the king of that revolution was Erwin Schrödinger. He wrote down an equation, the Schrödinger equation. It's beautiful. It tells us how the probability wave of an electron moves around an atom. It explains chemistry. It explains why the sky is blue, and it works beautifully as long as you're moving slow. But Schrödinger had a blind spot. He was ignoring the other giant in the room. He was ignoring Albert Einstein. Schrödinger's equation describes the world as if time and space are separate things. It's a non-relativistic equation. It assumes that if you kick a particle, it just moves faster. But Einstein taught us that's wrong. If things move fast, near the speed of light, time gets squashed, space gets squeezed, and mass gets heavy. So we had a marriage problem. We had quantum mechanics, the theory of the very small. And we had special relativity, the theory of the very fast. And they hated each other. Every time we tried to combine them, the mathematics exploded. Why is this a problem? Let me give you a scenario. And this is where the concept of energy really shows its teeth. Suppose I take two electrons, then I smash them together, I really whack them, I accelerate them until they are moving at 99.9% the speed of light, and bang. According to good old Schrödinger, what happens? Well, they bounce, maybe they deflect. But at the end of the day, you start with two electrons, you end with two electrons. The number of players on the field is conserved. But Einstein comes along and whispers in our ear, E equals mc squared. Energy is matter. Matter is energy. They are the same currency, just different denomination. So if I hit those electrons hard enough, if I pump enough kinetic energy into that collision, that energy doesn't just disappear. It can condense. It can freeze into matter. Out of that collision, I don't just get the two original electrons. Pop! Suddenly, a positron and an electron appear out of nowhere, or maybe a muon or a pion. I start with two particles. I end up with 4 or 6. Now look at Schrödinger's equation. It has a variable for particle 1 and particle 2. It tracks them, but suddenly particle 3 and particle 4 show up. The equation looks at them and says, who are you? I don't have a variable for you. The equation breaks. It coughs and dies. It cannot handle a world where the number of particles changes. This is a catastrophe, because in the real world, in the high-energy world inside the sun and the accelerators we built, particles are born and die every fraction of a second. Particles are not permanent. They are transient. So to fix this, as to marry the small and the fast, we had to throw away our idea of what a particle is. We had to change our philosophy entirely. We used to think of the electron as a little hard marble, a tiny point with a serial number on it. I am electron number 42, and we thought the world was made of a box of these marbles shaking around. That picture is wrong. It is fundamentally incompatible with relativity. To make physics work, we had to introduce the concept of the field. We must stop thinking of the electron as a thing. We must start thinking of the electron field. Now, what do I mean by that? I don't mean a force field like in the sci-fi movies that stops a laser blast. I'm something much more like, well, look at the air in this room. Consider the temperature. Right here, near my nose, the temperature is maybe 72 degrees. Over there by the door, maybe it's 70 degrees. Every single point in this room has a number associated with it. We call that a scalar field. Now ask yourself, is there a temperature particle flying around? Is there a little mosquito called 72 degrees buzzing from my nose to the door? No, of course not. The temperature is a property of the space. It is a value assigned to every point. This is how you must imagine the electron. There is an electron field that fills the entire universe. It is everywhere. It's inside you. It's inside the rock. It's inside the empty space between the stars. It is a fluid, a medium. So what is a particle? What is this thing we call an electron? An electron is just a ripple in that field. It is a knot. It is a place where the field value is high. If I have a calm lake, that's the vacuum. If I slap the water, I make a splash. That splash travels across the lake. You point at the splash and say, look, there is a particle, and this solves our marriage problem. This solves the Einstein problem. Why? Because if I have enough energy, if I slap the water hard enough, I can make 2 splashes. I can make 3 splashes. I haven't created new matter out of magic. I have just transferred energy from my hand into the field, and the field has excited itself into 2 new ripples. This is the shift. The particles, the electrons, the quarks, the photon, they are not the fundamental ingredients of the universe. The fields are the ingredients. The particles are just the temporary energetic states of those fields. They are the music. The fields are the guitar strings. And once you accept this, once you realize that you are not made of marbles, but you are made of interfering waves in a quantum ocean, then and only then can we understand how light and matter talk to each other, because they aren't crashing into each other. They are resonating. They are humming the same tune. Okay, so we have established that the universe is not made of particles. It is made of fields. But that word field is abstract. It's mathematical. We need a picture. We need something to hold on to in our mind. I want you to imagine a mattress, a giant infinite bed spring. Imagine a grid that fills the entire universe. Every point in space, here, there, behind the moon, is a little mass. And every mass is connected to its neighbor by a spring. Now, this is a model. Of course, there are no rusty metal coils in the vacuum, but mathematically, this is exactly what a free field is. Now, what happens if I jump on the corner of this mattress? If I kick this little mass right here? It moves down, but it's attached to the guy next to him, so it pulls him down, and he pulls the next guy, and the next guy pushes back. The disturbance doesn't stay put. It travels. A ripple spreads out across the bed springs of mine. If you look at the ocean, that ripple is a water wave. If you look at this mattress, that ripple is a sound wave. But if you look at the electromagnetic field, that ripple, that propagating disturbance, that is what we call light. Now, we have to quantize the mattress. We have to apply Heisenberg's rules to these springs. And the math tells us something shocking. Feynman, you are not allowed to wiggle the spring by any amount you want. Think of it like money. In the classical world, energy is like water. You can pour any amount. In the quantum world, energy is like pennies. You can give me 1 penny, you can give me 2 pennies, but you cannot give me 1.5 pennies. It's forbidden. So, looking at our mattress, the energy of the wave comes in chunks, discrete packets. There is a minimum size for the ripple. If I want to excite the electromagnetic mattress, I cannot make a ripple smaller than one chunk. And if I want to make it bigger, I have to add exactly one more chunk, then another. What do we call that minimum chunk? What is the smallest possible ripple you can make on the electromagnetic field? We call it a photon. What is the smallest possible ripple on the electron field? We call it an electron. This is the great revelation. Particles are not separate things. A particle is just the name we give to the unit of energy of the field. It is the quantization of the wiggle. Now, here is where it gets interesting, because our universe is not run by one mattress. It is run by a whole menagerie of them, all jumbled together and talking to each other. There is the UP quark field. In the down quark field, there is the muon field and the tau field and the neutrino fields, which are very shy. And for the forces, the photon field gives us light and electricity. But there is also the gluon field, which makes the strong force, and it is made of superglue. And the W and Z boson fields, which do the weak force responsible for radioactive decay. But there is one more, the most famous mattress of our time, the Higgs field. You see, for a long time we had a puzzle. Why do some of these ripples, these particles, have mass and others, like the photon, have none? Why is the electron so heavy compared to the neutrino, which is almost weightless? The answer is another field soaking all of space, the Higgs field. Think of it like a cosmic molasses or a vast crowd of invisible paparazzi. A photon ripples through this Higgs field and the paparazzi don't care. They ignore it. It zips through at the speed of light. It is massless. But an electron comes along. The paparazzi love it. They swarm around it. They stick to it. That interaction, that sticking, is what we experience as mass. The electron has to push through the crowd. It has inertia. So mass is not an intrinsic property. Mass is a measure of how much a particle interacts with the Higgs field. That was the missing piece. We found it, by golly. Now, how do we do the math for this menagerie with creation and annihilation operators, little machines? This little fellow here, a dagger, he is a creator. If I apply a dagger to the vacuum state, to the empty mattress, what does he do? He adds one unit of energy. Ping. He creates a particle. And this other fellow, A, without the dagger, he is the destroyer. He takes a unit of energy away. He annihilates a particle. Think of an elevator. The ground floor is the vacuum state. If I hit the up button, that's a dagger, the elevator goes up one floor. Now we have one photon, I hit it again. Two photons, I hit the down button, that's A, and we go down a floor. One photon disappears. So the whole universe, this incredibly complex dance, it is just a game of putting marbles in cups and taking them out. The cups are the modes of the field. The marbles are the particle. This simplifies our life enormously. We stop worrying about waves spreading out everywhere. We just count. One photon here, two electrons there. We turn calculus into algebra. And that is a very good trait. But there is a catch. There is always a catch. What happens when these particles interact? What happens when an electron ripple meets a photon ripple? To answer that, we need to draw some funny pictures. Now, we have these operators, we have these elevators creating and destroying particles, but we have a problem. The electron mattress and the photon mattress, they don't live in separate rooms. They occupy the exact same space. They are right on top of each other. And the most important thing about the universe is that these mattresses are tied together. They are linked. We call this coupling. How does an electron know another electron is there? They don't touch. They don't have eyes. If I have an electron here and another one over there, how does the force get from A to B? The answer is that the electron mattress is coupled to the photon mattress. When the electron wiggles, it shakes the springs of the electromagnetic field. It tickles it, and that tickle spreads out. I got tired of doing the algebra for this. It was a mess, pages and pages of indices. So I started drawing pictures, funny little doodles. Some people thought I was crazy, but it turns out the pictures are the math. Let's draw a map of a collision. We need rules. Rule number 1, time goes up. The bottom of the board is the past. The top is the future. Rule number 2, Space goes sideways. So here at the bottom, we have two electrons coming in. Electron 1 and electron 2. They are moving toward each other. Now, they don't hit like billiard balls. They don't touch. What happens is that at some moment, electron 1 shudders. It interacts with the field. It emits a photon, a squiggly line here. Now, pay attention. Electron 1 recoils. It changes direction. And this photon, it travels across the gap and smack it hits electron 2. Electron 2 absorbs it and gets pushed away. So the picture is two straight lines, a squiggly line across, and then the straight lines fly apart. Think of it like two skaters on a frozen lake, perfectly smooth ice. You are on skates, I am on skates. We are gliding toward each other, but we aren't allowed to touch. But I am holding a heavy medicine ball. When I get close to you, I throw the ball at you. Oof! The act of throwing it pushes me back. Conservation of momentum. I recoil. Then the ball flies through the air. That's the photon, and you catch it. Oof! The impact pushes you back. You recoil. To someone watching from a helicopter who can't see the ball, it looks like a magical force pushed us apart. But down here, we know the truth. We exchanged a particle. That is the origin of the force. All forces are just games of catch. But here is where nature gets sneaky. Here is where the accountant cooks the books. This photon in the middle, can I catch it? If I put a detector between the electrons, will I see a flash of light? No, you will not. This is a ghost. We call it a virtual particle. You see, Heisenberg gave us that uncertainty rule. Delta E times delta T is greater than or equal to h bar over 2. Usually, we think that limits what we can measure, but it also allows nature to cheat. It says you can borrow energy, you can violate the conservation of energy, you can create a photon out of nothing. But there is a condition. The bank is very strict. The more energy you borrow, the faster you must pay it back. This virtual photon exists for such a short time that it doesn't have to obey the rule E equals mc squared. It can have the wrong mass. It can have the wrong speed. It is off the books. It exists just long enough to carry the message from one electron to the other, and then poof, it's gone. The debt is paid. These virtual particles, they are the glue of the universe. The empty space around you is swarming with them, popping in and out of existence, borrowing from the bank and paying it back before you can catch them. Now look at this. Suppose I draw a line that goes down the board, backward in time. You say, Feynman, that's ridiculous. Nothing goes backward in time. That's science fiction. But look at the math. The equation for an electron moving forward in time with negative charge is mathematically identical. I mean exactly the same as a particle with positive charge moving backward in time. This isn't just a trick. This is real. An electron going backward in time is a positron going forward in time. This solves the mystery of antimatter. Why does every particle have an antiparticle? Because time is symmetric in the equations. If you take a movie of an electron and run it backward, you don't see an electron simply moving in reverse. You see a positron. So when we see a particle and an antiparticle collide and annihilate, in my diagrams, that's just one particle changing direction in time. It was going forward, it got hit, and it turned around to go back to the past. It's a beautiful unification. We don't need a new theory for antimatter. It's just the same actor walking the other way on the stage. But as beautiful as these pictures are, when we first tried to calculate the answer, the precise force between these electrons, we ran into a catastrophe, a disaster. The answer didn't come out to be a nice number. It came out to be infinity. And you can't build a universe out of infinities. So we had these infinities, and this is the great paradox of our theory. It predicts infinities, but it also gives us a trick to get rid of them, a magic trick. We call it renormalization. Now, what does that mean? Imagine you are buying a suit from a very strange tailor. The suit he gives you has sleeves 10 feet long. The pants drag on the ground for a mile. It's infinitely ill-fitting. But then he says, wait, I have adjustment dials. And he turns a dial marked mass and a dial marked charge. And as he turns them, the sleeves shrink, the pants rise. He tweaks these dials until the suit fits you perfectly. That's renormalization. We accept that the raw, naked electron, the one at the heart of all those virtual particles, has an infinite mass and charge, nonsense numbers. But we never see that electron. We only see the electron dressed in its cloud of virtual photons and particles. The infinities are hidden in that invisible, naked core. The dials we turn, the mass and charge we plug into our equations, are not the infinite naked ones. They are the finite, dressed up values we measure in the lab. We adjust the theory to fit the world. And the miracle is, it works. When we do this for quantum electrodynamics, we get the most precise predictions in the history of science. We can calculate the magnetic moment of the electron to 10 decimal places, and it agrees with experiment perfectly. It feels like a trick. It feels like cheating. But the universe seems to allow it. It's as if nature is saying, the infinities are my problem, not yours. You just measure the net result. But not all theories are so kind. We have one force that refuses this trick, gravity. When we try to make a quantum mattress for gravity, for the graviton, the infinities that come up are monstrous. We can't sweep them under the rug. The dials break, our trick fails. Einstein's beautiful curved space-time and our jiggling quantum matrices, they are at WAR. And we still don't know how to make peace between them. Maybe we need strings. Maybe we need loops. That's a fight for another day. So where does that leave us? We have built this incredible machine, the standard model. We have the quark fields, the lepton fields, the force fields, and the Higgs field. We have these mathematical matrices vibrating and exchanging ghosts, and it works. You might think we are done. You might think, Professor, we have the map of the universe. We can pack up and go home. But I have to warn you, do not get too proud. First, gravity is still out there, laughing at us. And second, remember the box. Remember the empty shoebox in the zero-point energy. I told you there was infinite energy in the vacuum. Well, we now know that this vacuum energy, this energy of nothing, is not zero. It is a tiny, tiny number, but it is not zero. And it is making the universe expand faster and faster. The astronomers call it dark energy. It is 95% of the universe, and we don't know what it is. And when we compare the number we measure for this dark energy to the number we calculate from our quantum mattress, do you know how close we are? We are off by 10 to the power of 120, one with 120 zeros after it. It is still and always the worst prediction in the history of science. So there is a mystery, a deep mystery. We are clearly missing a piece of the puzzle. Maybe supersymmetry, maybe strings, maybe something we haven't even dreamed of. And people ask me, does this bother you, Feynman? Does it bother you that you don't know the answer? I say, no, not at all. I think it's much more interesting to live not knowing than to have answers which might be wrong. I have a friend who is an artist, and he said, I look at a flower and I see the beauty. You scientists pull it apart and it becomes a dull thing. I think he is kind of nutty. Because I see the beauty he sees, but I see more. I see the cells. I see the molecular interactions. I see the quantum fields vibrating inside the petals to make the color red. Nature is like an onion. We peel a layer, that's classical mechanics. It looks complete. Then we find a problem, so we peel another layer, quantum mechanics. Then we find another, quantum field theory, then the Higgs. Is there a core? Is there a fundamental seed at the bottom, a final equation that fits on a t-shirt and explains everything, or is it just layers all the way down? Is it onions? Forever? I don't know. Nobody knows, and that is the fun of it. If we knew everything, there would be nothing left to do. The pleasure, the real pleasure, is in the finding things out. So go home. Look at the empty space in your room, and remember, it's not empty. It's jiggling. It's alive with fields and virtual ghosts and Higgs paparazzi, and it's waiting for you to figure it out. Thank you. Today's question is, what lies beyond the observable universe? Well, let's think about what that even means. Before we can ask what is beyond something, we have to understand where the boundary of that thing is and why there is a boundary at all. You hear this phrase a lot, the observable universe. And it sounds like There is a big fence out there in space with a sign hanging on it that says, "Do not cross, nothing to see past this point." But nature does not build fences like that. To understand what is actually going on, we have to start with something very simple, something you experience every single day. The act of seeing. How do you see anything? Suppose you're looking at your hand. You might think you just see it instantly, but you do not. What is actually happening is that light from a lamp or from the sun is coming down, hitting your hand, bouncing off and traveling into your eye. It goes through the lens, hits the retina at the back, triggers some electrical signals, and your brain says, "Ah, a hand." The crucial part of this process is that the light has to travel from the object to your eye, and traveling takes time. Now, for everyday objects, this time delay is so incredibly tiny that we do not even notice it. Light is extremely fast. It goes about 300,000 kilometers every single second. So when you look at someone sitting across the room, you're not seeing them exactly as they are right this instant. You are seeing them as they were a few billionths of a second ago. They could have disappeared completely in that billionth of a second, and you would not know it yet. For all practical purposes on Earth, we can ignore this delay. But when we look up at the sky, the distances become so enormous that we can no longer ignore how long it takes light to travel. Let us look at the moon. The moon is about 380,000 kilometers away. Since light travels at 300,000 kilometers per second, it takes a little over 1 second for the light from the moon to reach us. So you never see the moon as it is right now. You see it as it was about a second and a quarter ago. If somebody were to blow up the moon, we would not know about it for over a second. We would just be looking at a perfectly happy moon until the light of the explosion finally arrived. Let us go further out. The sun is much farther away, It takes light about 8 minutes to get from the sun to the earth. If the sun were to suddenly wink out of existence, we would still have 8 minutes of daylight, 8 minutes of gravity, 8 minutes of normal life before the darkness hit us. When you look at the sunset, you are looking at a ghost. The sun has already dipped below the horizon physically, but the light is still arriving. Now look at the stars at night. The nearest star system to us, Alpha Centauri, is so far away that it takes light over 4 years to get here. We say it is 4 light years away. When you look at Alpha Centauri, you are seeing it as it was 4 years ago, and you are looking into the past. If you look at the Andromeda galaxy, the nearest large spiral galaxy to our own Milky Way, you are seeing light that has been traveling for 2.5 million years. That light began its journey before modern humans even existed on Earth. It has been flying through empty space all that time just to finally hit your retina. So every time you look out into space, you are essentially looking back in time. The further out you look, the further back in time you are looking. There is no way around this. It is a strict rule of nature. Information cannot travel faster than light. Now let us follow this logical chain as far as it can go. If looking further away means looking further back in time, what happens if we look so far away that we look all the way back to the beginning of the universe? We know the universe had a beginning. We have gathered quite a bit of evidence that tells us the universe has been expanding for about 13.8 billion years. But it started from a very hot, very dense state, and it has been cooling and spreading out ever since. We call this beginning the Big Bang. So if the universe is 13.8 billion years old, that means light has only had 13.8 billion years to travel. If there is a galaxy so far away that it would take 20 billion years for its light to reach us, we simply cannot see it. The light has not had enough time to get here yet. It is still on its way. This is the fundamental reason why there is an observable universe. The boundary is not a physical wall in space. It is a wall in time. We are surrounded by a bubble of visibility, and the radius of that bubble is determined by the age of the universe and the speed of light. But we have to be careful here because things are a little more complicated than just multiplying 13.8 billion years by the speed of light, you might assume that the observable universe is a sphere with a radius of 13.8 billion light years. But it is not. It is actually much larger. It is about 46 billion light years in radius. How can that be? How can we see something 46 billion light years away if the universe is only 13.8 billion years old? Did the light travel faster than the speed of light? No. Light always obeys the speed limit. The trick is that the space between us and that distant object has been expanding while the light was traveling. Let us try to picture this. Imagine a little bug crawling on a rubber band. The bug is light, and its crawling speed is the speed of light. The rubber band is space. The bug starts crawling towards you from a distant spot on the rubber band. If the rubber band were just sitting there, the bug would reach you in a certain amount of time. But suppose while the bug is crawling towards you, somebody is stretching the rubber band. The bug is still making progress over the rubber band, but the total distance between its starting point and you is growing. By the time the bug finally reaches you, the spot where it started has been carried very far away by the stretching. This is exactly what happens with light in our universe. A photon of light left a very distant patch of space 13.8 billion years ago and headed towards us. As it traveled, the universe expanded, stretching the space out. The photon kept moving through that expanding space, making progress, and finally it hits our telescopes today. But if we ask, where is the physical stuff that emitted that photon right now, we have to account for all the stretching that happened over 13.8 billion years. That stuff has been carried far away by the expansion, and today it is located about 46 billion light years away from us. So our observable universe is a sphere, roughly 92 billion light years across. Everything inside this sphere is stuff whose light has had enough time to reach us. Everything outside this sphere is stuff whose light has not reached us yet. The boundary is called the cosmological horizon. Now we get to the core of the problem. What is past that horizon? What lies beyond the observable universe? Since we cannot see past it, we cannot just point the telescope and check the light has not arrived. No signal, no gravity, no information of any kind can reach us from beyond that line. So you might think science just has to stop right there. You might think we have to throw up our hands and say, we do not know and we can never know. But physicists are a stubborn bunch and we do not like to just give up. Even though we cannot observe what is beyond the horizon directly, we can use the laws of physics that we observe inside our bubble to make highly educated logical deductions about what is outside it. We have to look carefully at the clues left within our reach to understand the larger context. The first and most important clue is how the universe behaves near the edge of our observable bubble. What do we actually see when we look as far away as possible? If you build a very powerful telescope, like the James Webb Space Telescope or the Hubble Space Telescope, and you look deep into space, you see galaxies. You see billions of them. And as you look further away, the galaxies look younger. They look smaller, messier, and bluer because they are just forming. If you look even further, past the oldest galaxies, you might expect to just see empty space. But you do not. Instead, you see a wall. Not a wall of bricks, but a wall of glowing fog. It is called the cosmic microwave background radiation, or the CMB. This fog is everywhere. No matter which direction you look in the sky, if you look far enough, you hit this background glow. What is this fog? To understand it, we have to think about what the universe was like when it was very small. When the universe was small, all the matter in it was squeezed together. And when you squeeze a gas, it gets hot. The early universe was incredibly hot and dense. It was so hot that atoms could not even hold themselves together. An atom is usually made of a nucleus with electrons buzzing around it. But if the temperature is hot enough, the atoms smash into each other so violently that the electrons get knocked right off. You end up with a soup of freely roaming electrons and nuclei. This kind of soup is called a plasma. Now, plasmas have a very interesting property. They are opaque to light. Light consists of little packets of energy called photons. In a plasma, there are so many loose electrons flying around that a photon cannot go very far before it crashes into one. The photon gets absorbed, re-emitted, and bounced in a random direction. It is like trying to run through a dense crowd of people while blindfolded. You keep bumping into people and changing direction. You cannot walk in a straight line. Because the photons could not travel in straight lines, the early universe was filled with light, but you could not see through it. It was like being inside a glowing white-hot cloud of fog. But the universe was expanding it, and as it expanded, it cooled down, the temperature dropped and dropped. Finally, about 380,000 years after the Big Bang, the universe cooled enough for something magical to happen. The temperature dropped below the point where atoms are ripped apart. Suddenly, the flying electrons slowed down enough to be captured by the nuclei. They formed neutral atoms, mostly hydrogen and helium. And neutral atoms do not block light the way free electrons do. All the electrons were suddenly locked up. The crowd of people vanished, and the space between the atoms became clear. The photons that had been bouncing around were suddenly free to fly in a straight line. The fog lifted. Those exact same photons, the ones that were freed 380,000 years after the Big Bang, have been flying through empty space ever since. They have been flying for over 13 billion years, and some of them are hitting our radio telescopes right now. Because the universe has expanded so much since then, the wavelengths of those photons have been stretched out. They started as incredibly energetic visible light, but they have been stretched into microwave radiation. That is the cosmic microwave background. When we map this microwave background, we are looking at the actual edge of our observable universe. We are looking at the baby picture of the cosmos. We cannot see past it using light, because before that moment, the universe was opaque. The light was trapped. So we are stuck inside this sphere. But notice something very important about this sphere. It is not a boundary of physical stuff. The plasma fog we see in the distance is not located at a specific place in space. It is a moment in time. The stuff that emitted that fog is still out there. It did not disappear. It just evolved. The plasma cooled down, formed atoms, clumped together into stars, gathered into galaxies, and probably formed planets. In fact, if there is a civilization living in one of the galaxies that formed from the plasma we see at the edge of our observable universe, they are looking back at us right now. But they do not see our solar system, and they do not see the Earth. Our light has not had time to reach them yet. When they look in our direction, they see us as we were 13.8 billion years ago. They see the plasma fog that our local region of space used to be. Our observable universe is centered on us. Their observable universe is centered on them. The two spheres overlap, but they are not the same. This realization leads us to a very powerful scientific principle called the cosmological principle. It is really just an extension of the Copernican principle. Copernicus was the fellow who figured out that the Earth is not the center of the solar system. We are just another planet going around the sun. Later, astronomers realized the sun is not the center of the Milky Way galaxy. It is just an average star out in the suburbs. And our Milky Way is not the center of the universe. It is just one galaxy among billion down. The cosmological principle takes this idea to its logical conclusion. It states that on a very large scale, the universe is homogeneous and isotropic. Homogeneous means it is the same everywhere. Isotropic means it looks the same in every direction. When we look out into our observable universe, this principle holds up incredibly well. If you take a large enough box of space, say a few 100 million light years across, and you count the galaxies in it, and then you take another box of the same size somewhere else, you will find roughly the same number of galaxies. The overall texture of the universe is uniform. The cosmic microwave background is also incredibly uniform. Its temperature is the same everywhere to within a few parts in 100,000 above. So what does this tell us about what is beyond our observable bubble? It tells us that the most reasonable logical assumption is that it is just more of the same. There is absolutely no physical reason to think that the universe ends right where our vision happens to run out. That would be absurd. It would be like standing in the middle of the ocean, looking at the horizon and assuming the water turns into a giant brick wall, right where it meets the sky. The horizon is just a limit of your sight, dictated by the curvature of the earth. If you sail to the horizon, you just see more ocean. Similarly, our cosmic horizon is dictated by the speed of light and the age of the universe. And if you could somehow magically teleport to a galaxy 40 billion light years away, right at the edge of our observable universe, you would not find a wall. You would just look around and see a universe very much like ours. You would see galaxies in all directions. You would see a cosmic microwave background. You would be in the center of your own new observable universe with a new horizon, another 46 billion light years away. So the first and most grounded answer to the question, what lies beyond the observable universe, is more universe, more galaxies, more stars, more planets, more black holes, operating under the exact same laws of physics that we see here. But this simple answer immediately raises a much more difficult question. If there is more universe out there, how much more? Does it go on forever? Is the universe infinite, or is it finite but just very large? To answer this, we have to figure out the shape of space. Now, this is where things get a bit strange, so we have to go slowly. When I say the shape of space, I am not talking about the objects in space. I am talking about the geometry of the vacuum itself. Imagine you are a two-dimensional creature living on the surface of a shape. You cannot look up or down. You can only move forward, backwards, left and right. If you live on a completely flat piece of paper that goes on forever, your world follows the rules of geometry you learned in school. Euclid's geometry. If you draw two parallel lines, they will stay exactly the same distance apart forever. They will never cross. If you draw a triangle and add up the three inside angles, they will always add up to exactly 180 degrees. We call this flat geometry. But what if you live on the surface of a sphere, like the Earth? You are still a two-dimensional creature, so you just feel like you are walking on a flat surface. But if you start doing geometry, you notice something weird. Suppose you start at the equator, and you and a friend stand a few miles apart. You both face perfectly due north, so your paths are parallel. You both start walking straight forward. As you walk toward the North Pole, you will start getting closer and closer together until you bump into each other at the pole. Your parallel lines crossed. And what about triangles? Suppose you draw a line from the North Pole down to the equator. That is one side. Then you make a sharp 90-degree turn and walk along the equator. That is the second side. Then you make another sharp 90-degree turn and walk back up to the North Pole. You have made a triangle. But look at the angles. You have two 90-degree angles at the equator, plus whatever angle you made at the pole. The angles add up to more than 180 degrees, and this happens because the space you are living in has positive curvature. It is bent closed. A closed, positively curved surface is finite. It has a limited area, but it has no edge. You can walk forever and never fall off, but you will eventually circle back to where you started. There is a third option. Imagine the surface of a saddle or a potato chip. If you draw a triangle there, the angles will add up to less than 180 degrees. Parallel lines will spread apart from each other. This is called negative curvature or an open geometry. Like a flat plane, a negatively curved space can go on forever. Einstein's theory of general relativity tells us that our three-dimensional space can have these same kinds of curvature. The presence of matter and energy bends space, but there is also a global overall curvature to the entire universe. If the universe has positive curvature, it curves back on itself like a three-dimensional sphere. It would be finite. If you flew a spaceship in a straight line for long enough, you would eventually arrive back at Earth. If it has zero curvature, it is perfectly flat. If it has negative curvature, it is shaped like a three-dimensional saddle. Both flat and saddle-shaped universes can be infinite. So how do we figure out which one we live in? We measure a triangle. Of course, we cannot just draw a giant triangle with string and space. We need a triangle that is already there, one that is big enough to show the curvature of the cosmos. Fortunately, the universe provided one for us right at the edge of the observable universe, the cosmic microwave background. When we look at the map of the CMB, it is not perfectly smooth. There are tiny, tiny variations in temperature. Some spots are a fraction of a degree warmer, some are a fraction of a degree cooler. These spots are the result of sound waves that were bouncing around in the plasma of the early universe. Physics tells us exactly how big these spots should be in physical psi. We know the physics of that plasma very well. It is just fluid dynamics and thermodynamics. We know that the typical hot spot should have a specific physical width. So we have a triangle. One side is the physical width of the hot spot, which we know. The other two sides are the lines of light traveling from the edges of that spot all the way to our telescopes on Earth. We know the distance to the CMB, so we know how long those lines are. Now we look at the angle that spot takes up in our sky. If space is perfectly flat, the light rays travel in perfectly straight lines, and the spot should look to be about 1 degree across in our sky. If space is positively curved like a magnifying glass, the light rays would be bent inward, and the spot would look bigger than 1 degree. If space is negatively curved, the light rays would be spread out, and the spot would look smaller than 1 degree. Astronomers sent satellites into space like WMAP and Planck to measure these spots with incredible precision. They looked at the angles, they did the math, and what did they find? The spots are exactly 1 degree across to within a margin of error of less than 0.5%. The universe appears to be perfectly flat. Now, this is a very profound measurement. If the universe is perfectly flat, then ordinary geometry applies. Parallel lines stay parallel, and a perfectly flat geometry suggests that the universe goes on forever. It suggests that space is infinite. If this is true, then what lies beyond the observable universe is simply an infinite expanse of more galaxies, more stars, more planets. It goes on without end. But we have to be extremely careful here. We must not jump to conclusions. We measured the curvature of the observable universe, and we found it to be flat within our margin of error. But that does not definitively prove the entire universe is flat, nor does it prove it is infinite. Think about standing on a frozen lake. You look around, and the ice looks perfectly flat. You take out a surveyor's laser, you measure the surface over a mile, and it looks perfectly flat. Does that mean the Earth is flat and infinite? No, the Earth is a sphere, but the sphere is so large that a small patch of it appears flat to your limited instrument. The exact same thing could be true of our universe. That it might have a slight positive curvature, meaning it eventually wraps around on itself, but the curve is so gentle that we cannot detect it within our limited observable bubble. If the entire universe is a sphere that is 1,000 times bigger than our observable bubble, the piece we can see would look completely flat to us. Furthermore, even if the universe is perfectly flat mathematically, it does not strictly have to be infinite. This brings us to a branch of mathematics called topology. Geometry tells you how space curves. Topology tells you how space is connected. Imagine taking a flat piece of paper. It has zero curvature. Now roll it up into a cylinder and tape the edges together. The surface of that cylinder is still intrinsically flat. If you draw a triangle on the cylinder, the angles still add up to 180 degrees. Now imagine taking the two ends of the cylinder and bending them around to connect them, making a donut shape. A mathematician calls this a torus. A torus can be constructed in such a way that it remains perfectly flat intrinsically, If you live inside a flat torus, your space has no curvature. Light travels in straight lines, but the space is finite. If you walk in a straight line, you will eventually circle around the torus and come back to where you started. It is like the screen in the old video game Pac-Man. When Pac-Man goes off the right edge of the screen, he instantly reappears on the left edge. The top is connected to the bottom one. The screen is perfectly flat, but it is finite. It wraps around. Could our universe be like a three-dimensional Pac-Man screen? Could it be flat, but mathematically connected in a way that makes it finite? Physicists have actually looked for evidence of this. If the universe wraps around and it is smaller than the observable universe, we should see the same things in different parts of the sky. We would be seeing multiple images of the same galaxy, just from light that traveled around the universe in different directions. We would look in one direction and see a cluster of galaxies and look in the opposite direction and see the exact same cluster from the other side. We have searched the sky for these repeating patterns, especially in the cosmic microwave background. We looked for identical circles of temperature variations on opposite sides of the sky. We found nothing. No repeating pattern, and no mirrored images. This tells us that if the universe does wrap around like a torus, the loop is bigger than our observable universe. The edges of the Pac-Man screen are further away than our light can reach. We cannot rule it out, but we have no evidence for it. So based on the best measurements we have, the universe is flat, and it is most likely vastly larger than what we can see, quite possibly infinite, but it should be. But why is it flat? And why is the cosmic microwave background so incredibly uniform? This is a puzzle that bothered physicists for a long time. It is called the horizon problem. I mentioned earlier that the temperature of the CMB is the same everywhere. If you look at a patch of the sky in the north, it is 2.7 degrees above absolute zero. If you look at a patch of the sky in the south, it is 2.7 degrees above absolute zero. Why is that strange? Suppose you take a cup of hot coffee and a glass of ice water and you put them on opposite ends of a long table. Are they going to be the same temperature? No. The only way they become the same temperature is if you mix them together, or if you wait a very long time for the heat to transfer through the room. They have to interact to balance their temperatures. In the early universe, those regions of space in the north and the south were expanding away from each other very rapidly. When the universe was 380,000 years old, those regions were so far apart that light had not had enough time to travel between them since the Big Bang. They were outside of each other's observable universes. They had no way to communicate. They had no way to mix or transfer heat. If they had never interacted, why would they be exactly the same temperature? It would be like rolling a billion dice and having them all come up as sixes by pure coincidence. It does not make sense, and there had to be a mechanism that made them the same temperature. In the 1980s, a physicist named Alan Guth proposed a solution. He suggested a theory called cosmic inflation. Inflation says that very, very early in the history of the universe, a tiny fraction of a second after the Big Bang, space underwent a period of exponential, incredibly violent expansion. It did not just expand a little bit, it stretched by a factor of at least 10 to the 26th power in less time than it takes to blink. Let us picture what that means. Imagine a region of space the size of a single proton. Before inflation, that region had plenty of time to mix, slosh around, and reach a uniform temperature. It was all connected. Then inflation hit. Space stretched so fast that this tiny uniform region was blown up to become much, much larger than our entire observable universe. Because our observable bubble is just a microscopic speck inside this inflated region, everything we can see looks uniform. The north sky and the south sky are the same temperature because long before the plasma fog, before the stars, before anything, they were crammed right next to each other, sharing heat. Inflation simply ripped them apart and spread them out, Inflation also solves the flatness problem. Imagine taking a wrinkled balloon. If you blow it up to the size of the Earth, the surface will look perfectly flat to an ant walking on it. Inflation stretched the fabric of space so violently that any initial wrinkles or curvature were ironed out completely flat. Now, inflation is a very successful theory. It explains the uniformity we see. It explains the flatness we see. It even explains those tiny variations in the CMB, the ones that eventually formed galaxies. It says those spots are quantum fluctuation, tiny jitters in the energy of empty space that got stretched to cosmic sizes during the rapid expansion. But if inflation is correct, it has profound implications for what lies beyond our observable universe. It means the total universe is unimaginably larger than the part we can see. If inflation stretched a proton-sized speck into something billions of times larger than our visible bubble, then the boundary of our vision is essentially nothing. It is a meaningless local line drawn by the speed of light, while the physical reality stretches on practically forever. The unobservable universe would just be a vast, expanding continuation of the matter and energy we see around us. But there is a twist. And this is where the physics gets deeply theoretical, and we have to tread carefully so we do not lose our grounding in logic. We have to ask, what caused inflation, and why did it stop? Physicists model inflation as being driven by a special kind of energy field called an inflaton field. You can think of this field like a ball rolling down a hill. When the ball is high on the hill, the field has a lot of energy. And this energy causes space to expand exponentially, That is the period of inflation. As the ball rolls down the hill, the energy drops, and inflation eventually stops. The energy from the field is dumped into space, creating all the hot particles and radiation that make up the Big Bang plasma. We call this process reheating. So, in our region of space, as the ball rolled to the bottom of the hill, inflation stopped, the Big Bang happened, and we got stars and galaxies. But quantum mechanics tells us that these fields are not perfectly smooth. They jitter. They have uncertainty. While the ball is trying to roll down the hill, quantum fluctuations are pushing it around. Sometimes they push it down faster, and sometimes they push it back up. In some regions of space, the quantum jitters might push the ball back up the hill, keeping the energy high. As there is in those regions, inflation keeps going. Space keeps stretching violently. Because space during inflation is expanding so incredibly fast, the regions where inflation continues will grow much, much faster than the regions where it stops. Space is being created at an unbelievable rate. This leads to a concept called eternal inflation. It suggests that inflation did not just happen once and stop everywhere. Instead, inflation is a continuous, eternal process happening in a vast underlying background, and space is constantly stretching at lightning speed. But here and there, the field drops to the bottom of the hill, and inflation stops in a localized bubble. Inside one of those bubbles, the energy turns into a hot plasma, and a normal universe begins to evolve. The bubble expands at a normal, slower rate. Our entire observable universe, all 92 billion light years of it, would be just a tiny fraction of one of these bubbles. The unobservable part of our universe would fill out the rest of our bubble. But outside our bubble, there is more inflating space stretching away forever. And within that inflating space, other bubbles are constantly forming. Bubbles upon bubbles upon bubbles. A multiverse. Now, you have to realize that this is not science fiction, and this is not someone sitting around making up a cool story. This is a mathematical consequence of combining the theory of inflation, which we need to explain what we see in our telescopes, with the rules of quantum mechanics, which we have tested extensively in our laboratories. When you put those two pieces of physics together, eternal inflation falls out of the equations almost unavoidably. So what lies beyond our observable universe in this scenario? So first, there is a vast amount of unobservable space that is part of our own bubble. This space would look very much like ours. It would have galaxies, CMB, the same laws of physics. We would never be able to reach it because the space between us and it is expanding, but it is there. But if you could somehow travel past the edge of our bubble, you would enter the realm of eternal inflation. You would find an intervening space that is expanding so violently that it would instantly rip you apart. And far beyond that, separated by uncrossable gulfs of rapidly expanding space, would be other bubble universes. And here is the most curious part. Are those other bubble universes the same as ours? Not necessarily. In physics, we know that many of the rules of nature, the things we measure and assume are constant, might just be historical accidents. The mass of the electron, the strength of gravity, the speed of light, why do they have the exact values they do? We do not know. According to some theories, like string theory, there are many possible ways the fundamental laws of physics can settle down when a universe is born. Think of water freezing into ice. As water freezes, it forms ice crystals. The molecules arrange themselves in a pattern. The pattern is driven by the laws of chemistry. But the exact orientation of the crystal, where the flaws are, what the specific shape looks like, can vary every time you freeze it. When a bubble universe stops inflating and cools down, the fundamental fields of nature freeze into a specific state. In our bubble, they froze in a way that gave us electrons, protons, 4 forces of nature, and 3 dimensions of space. But in another bubble far away, the fields might have frozen differently, or that universe might have 5 forces of nature. It might have no electrons. Gravity might be incredibly strong or so weak that matter cannot clump together. It might have 6 dimensions of space. If this idea, called the string theory landscape, is correct, then what lies beyond our observable universe is not just more of the same. It is everything that is physically possible. An infinite tapestry of universes, each with its own laws of physics completely disconnected from one another. Now I must stop here and be very clear about something. We have crossed a line in our reasoning. We started with the speed of light, which we can measure. We moved to the cosmic microwave background, which we can map. We used the expansion of space, which we can observe. We deduced the geometry of the universe from hard data. But when we talk about eternal inflation and multiverses, we are operating at the absolute bleeding edge of theoretical physics. We do not know if eternal inflation is true. We do not know if string theory is right. We cannot observe these other bubbles. By definition, light from them can never reach us. The inflating space between the bubbles pushes them apart faster than light could ever cross the gap. Some scientists argue that if a theory predicts something that can fundamentally never be observed or tested, it is no longer physics. It becomes philosophy. If we can never see the other bubbles, do they really exist in a scientific sense? This is a valid criticism. A good physicist must always be skeptical. We must demand proof. So is there any way to test what lies beyond our bubble? Is there any way to look past the plasma wall of the CMB? Actually, there might be. I said earlier that we cannot look past the CMB using light because the plasma was opaque to light. But light is not the only way information can travel. There is another kind of particle in nature called a neutrino. Neutrinos are ghost particles. They are incredibly light and they almost never interact with ordinary matter. Right now, trillions of neutrinos from the sun are passing through your body every second. They go straight through the Earth as if it were not even there. Because neutrinos hardly interact with anything, they were not blocked by the dense plasma of the early universe. The universe became transparent to neutrinos long before it became transparent to light. In fact, neutrinos could fly freely through space just 1 second after the Big Bang. If we could build a telescope capable of detecting these ancient neutrinos, and it would have to be incredibly sensitive, perhaps a detector the size of a planet, we could look back to 1 second after the Big Bang. We could see a neutrino map of the sky, just like the microwave map. This would give us a much clearer picture of the initial conditions of the universe and might provide clues about the physics of inflation. There is an even better messenger, gravitational wave. Gravitational waves are ripples in the fabric of space-time itself. When massive objects move violently, they warp space, and those warps travel outward at the speed of light. Albert Einstein predicted them in 1916, and we finally detected them directly in 2015 from black holes crashing together. Because gravitational waves are ripples in space itself, nothing can block them. No plasma, no matter how dense, can stop a gravitational wave. If the violent expansion of inflation happened, it should have generated an enormous amount of gravitational waves. These waves would have stretched and squeezed the fabric of the universe, and those ripples should still be echoing through space today. If we can detect the primordial gravitational waves from inflation, we can read the fingerprint of the Big Bang itself. We could measure exactly how fast inflation happened, how much energy was involved, and whether the quantum models that predict eternal inflation are on the right track. There is even a crazy idea that if our bubble universe collided with another bubble universe in the distant past, the collision would have left a giant circular bruise on the cosmic microwave background. Astronomers have looked for these collision rings. So far, they have found nothing conclusive, but the search continues. So we are trying it. We are pushing the limits of our engineering and our mathematics to peer as deeply into the dark as we possibly can. Let us summarize the chain of logic we have built. What lies beyond the observable universe? First, we know for a fact that there is space beyond our vision. The horizon is just the limit of light travel time, not a physical end. Just past that horizon, it is almost certainly a continuation of our own universe. More galaxies, more stars, more of the same physics. Second, based on the flatness of the space we can measure, this continuation is vastly larger than our observable bubble. And there is a very good chance it is completely infinite. We are a finite speck floating in an infinite ocean of stars. Third, the mechanism that explains the uniformity of our speck, cosmic inflation, suggests that our massive, possibly infinite universe might just be one localized bubble in a much larger, eternally expanding multiverse. Fourth, in that multiverse, the laws of physics themselves might mutate, meaning that far beyond our observable universe, the fundamental nature of reality might be completely alien. It is a humbling picture. We used to think the Earth was the whole world. Then we realized the solar system is vastly bigger. Then we found the Milky Way. Then we found billions of other galaxies. Every time we looked closer, the universe got bigger and we got smaller. Now we are staring at the edge of our observable bubble, and logic tells us that the pattern continues. The observable universe, with its 2 trillion galaxies, is just a local neighborhood. We do not have all the answers. We might never have all the answers. Nature does not owe us a complete explanation of herself. But the fun is in the figuring out. The joy of physics is taking what little we can see, testing it, prodding it, looking at the rules it follows, and using human reason to trace those rules out into the dark. We cannot see beyond the edge, but our minds can travel there. And what we find in our equations is a cosmos far more vast, far more wild, and far more interesting than anything we could have possibly invented. Keep looking up, keep asking why, and never assume that the limit of your vision is the limit of the world. Thank you. Today's lecture is What Happens After the Universe Ends. I walked outside a few nights ago in Pasadena. It was unusually clear. I looked up at Orion. You look at those massive stars and they seem permanent. They look like they'll just sit there forever. What? They won't. They're burning fuel. Every second, our sun takes about 600 million tons of hydrogen and smashes it together to make helium. 4 protons get squeezed until they stick. The new helium nucleus weighs just a tiny bit less than the 4 original protons. That missing mass turns into energy. E equals mc squared, and that energy pushes outward. It fights gravity. Gravity wants to crush the star. The nuclear fire pushes back. It's a balancing act, though, but you only have so much hydrogen. The tank empties. The core collapses. The pressure spikes. The temperature goes up until helium starts fusing into carbon, then oxygen, then neon. The star is desperately trying to keep the fire going to fight off gravity. It works its way up the periodic table. It stops at iron. Iron is the ash of the nuclear fire. You can't get energy by squeezing iron together. The star runs out of tricks. It collapses inward. For a star like our sun, it shrinks down until it's about the size of the Earth. 1,000,000 miles of gas crushed into a ball 8,000 miles wide. We call it a white dwarf. Why does it stop shrinking? Why doesn't gravity just crush it into nothing? It stops because of a weird rule in quantum mechanics. The Pauli exclusion principle. Two electrons refuse to be in the exact same state at the exact same time. They hate each other. Not just electrical repulsion, and it's a fundamental property of their identity. When you crush them together, they have to move faster to avoid occupying the same state. They zip around near the speed of light, and that violent motion creates pressure. Electron degeneracy pressure. Gravity pushes in. The angry electrons push out. The white dwarf sits there. It's dead. No more fusion, just a hot ember cooling off in the dark. We think about time in human terms, 100 years, 1,000 years. Let's think bigger, 1,000,000,000,000 years. The universe is about 13.8 billion years old right now. In 1,000,000,000,000 years old, the free gas clouds will be used up. No new stars will form. The galaxies will go dark. The night sky will be black. Just white dwarfs, neutron stars, and black holes drifting around. The white dwarfs will slowly cool down. They radiate their heat away into space. Space is big. Space is cold. The heat just leaves. The white dwarf turns from white to red, then to black, a black dwarf, a giant cold sphere of carbon the size of a planet. Drifting. This takes an agonizingly long time, maybe 100 trillion years. And eventually the universe is just black dwarf neutron stars and black holes. But let's look at that black dwarf. What is it made of? Protons, neutrons, electrons. Are they forever? I don't know for sure. Nobody does. I spent a year trying to calculate the exact decay rate of a proton using a simplified gauge theory, and I completely messed up the boundary conditions. I just couldn't get the cross-sections to match. The math gets incredibly messy when you try to force the strong and weak nuclear forces to talk to each other at high energies. But the equations hint that protons probably aren't permanent. In physics, if something isn't strictly forbidden by a conservation law, it usually happens eventually. We have theories that try to connect the strong nuclear force with the weak force and electromagnetism. As if they're right, the proton is fundamentally unstable. It's built out of three smaller things called quarks, two up quarks and a down quark. Those quarks are held together by gluons. Occasionally, very rarely, a quark might change its flavor. It might spit out a super heavy particle, an X boson. This boson lives for a fraction of a trillionth of a second. Then it decays into a positron, and the pion decays into photons. The positron annihilates with a nearby electron. More photons there. The proton is gone. It turned into light. How long does this take? We built giant tanks of water deep underground in Japan, 50,000 tons of ultra-pure water surrounded by photomultiplier tubes. And we waited for a single proton in that water to decay and give off a flash of light. We waited years. We didn't see a thing. That tells us the half-life of a proton must be longer than 10 to the 34th years. That's a 1 with 34 zeros after it. A tremendously long time, but not infinity. If protons decay, the black dwarfs will slowly evaporate. Over 10 to the 40 years, they turn into a thin mist of photons and electrons, a slow fizzle of light. in the total dark. What's left after the matter dissolves? Black holes. A black hole is just pure gravity. Space bent so tightly that light can't climb out of the hole. You throw a rock in, it's gone. Stephen Hawking realized black holes aren't completely black. Empty space isn't empty. It boils. The uncertainty principle says you can't know exactly how much energy is in a patch of space at a specific time. If you look at a very small time window, the energy can fluctuate wildly. These fluctuations create pairs of particles. An electron and a positron, they pop into existence out of the vacuum. They borrow energy from the universe. They exist for a tiny fraction of a second. Then they crash into each other and disappear. They pay the energy back. Virtual particles. This happens everywhere, right in front of your face. Put a black hole in the middle of this boiling vacuum. Put the event horizon right there, the boundary line where nothing can escape. A pair of particles pops into existence right on the razor edge of the horizon. One particle is slightly inside, the other is slightly outside. The one inside is trapped. It falls toward the center. The one outside is free. It flies away. They can't crash into each other. They can't annihilate. The borrowed energy has to be paid back. Where does it come from? It comes from the mass of the black hole. The black hole loses a tiny bit of mass to pay for the particle that escaped. The escaping particle is real. It's Hawking radiation. The black hole is glowing very faintly. It's leaking mass into space. As it loses mass, it gets smaller. As it gets smaller, the horizon curves more sharply. The radiation gets hotter. It leaks faster. For a black hole the mass of our sun, this radiation is incredibly cold. A 10 millionth of a degree above absolute zero. It's absorbing more heat from the background radiation of space than it gives off. It's actually growing right now, but the universe is expanding. Space is stretching. The background radiation is stretching with it. It's cooling down. Eventually, the universe will be colder than the black hole. Then the black hole starts losing the battle. It shrinks. Over 10 to the 100 years, a 1 with 100 zeros, a Google years, it shrinks down to the size of a mountain. Then a boulder. Then a single atom. It gets incredibly hot. At the very end, it explodes. It releases the energy of 1 billion nuclear bombs in a final flash of gamma rays. The problem with calculating the exact moment the black hole explodes, and I've stared at these equations until my eyes hurt, is that the geometry at the very end the math breaks down entirely. General relativity demands a singularity of infinite density. Quantum mechanics refuses to allow infinite density. The two theories crash into each other and give you nonsense. We need a theory of quantum gravity to know exactly what happens in the last microsecond. We don't have one, but whether it leaves a microscopic remnant or vanishes entirely, the giant black holes are gone. And this brings us to a phase that deeply bothers me. There's something genuinely irritating about a universe that just slowly stops. You spend your whole life figuring out the rules of the game, and the board just rusts away into a freezing fog. It feels like a bad joke. No stars, no planets, no black holes, just a few stray photons, an electron here, a positron there, separated by billions of light years. The universe is still expanding. Dark energy is pushing space apart faster and faster. For those stray photons get stretched by the expanding space. Their wavelength gets longer. Their frequency drops. Their energy drops. Temperature is just a measurement of how much energy things have. When the photons stretch out, their energy fades. The temperature of the universe drops. It approaches absolute zero. It never quite reaches it, but it gets asymptotically close. This is the heat death, maximum entropy. Let's think about entropy. Think about a hot cup of coffee in a cold room. The heat is concentrated in the cup. That's a state of low entropy. Over time, the heat moves from the coffee to the room air. It spreads out. The coffee cools down. the room warms up a tiny bit. Eventually, the coffee and the room are the exact same temperature, equilibrium. Nothing happens anymore. You can't run an engine on it. You need a difference in temperature to do work. You need a hot place and a cold place. When everything is the exact same temperature, no physical process can occur. That's the heat death of the universe. The energy hasn't disappeared. Energy is always conserved. It just smoothed itself out so perfectly that it became entirely useless. No hot spot, no cold spot, no flow of heat. Time effectively loses its meaning. If absolutely nothing changes, how do you measure time? A clock needs moving parts. A moving part requires an energy difference to push it. There are no energy differences left. You could wait 10 years or 10 trillion years and the universe would look exactly the identical same. Is that the end of the story? A freezing void expanding forever? Wait, let me go back to the vacuum. I skipped something. Empty space has a temperature. It's not strictly zero. Because of dark energy, space is expanding at an accelerating rate. That creates a horizon, just like a black hole has a horizon. There is a distance so far away that space is expanding away from us faster than light. We can never see past that line. That cosmological horizon produces a kind of thermal radiation, Gibbons-Hawking radiation. It means the empty vacuum of space has a minimum base temperature, about 10 to the minus 30 degrees, extremely cold, but mathematically greater than zero. Because the temperature isn't zero, there is still a tiny microscopic bit of thermal jitter. The void still boils softly. Think about what that implies. If you wait long enough, random thermal fluctuations will cause things to happen. Let's imagine a sealed box of gas. You have a box full of air molecules. They bounce around randomly. Usually they remain spread out evenly inside the box, but purely by chance, a few molecules might bounce and all end up in the left half of the box at the exact same moment. It's unlikely, but not impossible. If you wait long enough, eventually, all the molecules in the box will randomly bounce into one single corner. How long? A ridiculously long time. But in the late universe, we have nothing but time. We have infinity. In an infinite amount of time, any physical event with a probability greater than zero is guaranteed to happen. Out of the freezing vacuum, particles will randomly fluctuate into existence. Not just virtual particles that disappear immediately. Real particles, the background energy of the vacuum will randomly concentrate in one spot just by pure chance, a sudden localized flash of low entropy. It might create an electron. It might create a whole atom of hydrogen. If you wait even longer, it might create a macroscopic object. You might get a chunk of ice floating in the void. You might get a functioning pocket watch. You might get a human brain, complete with false memories of a life that never happened, floating in the vacuum for a fraction of a second before freezing to death. Ludwig Boltzmann thought about this in the 1800s. It's a disturbing statistical consequence of infinite time. If the universe is infinite and eternal, random thermal fluctuations should produce vastly more isolated floating brains than entirely structured logical universes like ours. By pure probability, you are mathematically far more likely to be a random fluctuation in a dead universe than a real person sitting in a room listening to a physics lecture. But you're probably not. I'm reasonably sure I'm standing in a real room. Why? Because the Boltzmann brain argument assumes the universe works like a simple closed box of gas forever. It might not. Let's think about the actual shape of space. What if the whole geometry just repeats? Henri Poincaré's proved a theorem in classical mechanics. If you have a closed system with a fixed amount of energy and it obeys the normal laws of physics, eventually it will return to its exact initial starting state. It might take 10 to the 10 to the 10 to the 10 years. But it will happen. Every particle will bounce off every other particle and eventually find its way back to the exact coordinates it started at. But our universe is expanding. It doesn't look like a closed box. Space is getting physically bigger. Roger Penrose looked at this problem. He looked at the math of the very early universe and the math of the very late universe. At the Big Bang, the universe is extremely hot, incredibly dense, and full of violent radiation. Particles are moving so fast that their mass hardly mattered. They behave exactly like light. In the deep, distant future, the universe is extremely cold, incredibly empty, and full of faint radiation. The black holes evaporated into light. The protons decayed into light. Everything is massless. Here is the mechanical trick. In physics, if a particle has no mass, it does not experience time. A photon moving at the speed of light doesn't have a ticking clock. From the photon's perspective, the moment it was created in a decaying star and the moment it hits a telescope mirror are the exact same frozen instant. If the universe contains absolutely nothing but massless radiation, there is no physical way to measure scale. There are no rulers. A ruler is made of atoms. Atoms have mass. You need mass to define a physical distance. You can't measure distance and you can't measure time. Then, mathematically, a vastly expanded, empty, infinitely cold universe becomes structurally identical to the infinitely small, hot, dense point of the Big Bang. The end becomes the beginning. Space forgets how big it is. The whole metric rescales. The infinite cold void becomes the singularity for a new universe, a new Big Bang. He calls it conformal, cyclic cosmology. Is it true? I don't know. People have looked for concentric rings in the cosmic microwave background, echoes of supermassive black holes from a previous universe crashing together and leaving gravitational scars on the next iteration. The data is incredibly noisy. Some people see the rings in the static. Most people don't. That's how experimental physics goes. You'll argue about the noise until someone builds a better satellite telescope. Let's drop the complicated cosmology for a minute and just look at the mechanics of space itself. And how exactly does space expand? People always use the balloon analogy. They tell you to imagine dots drawn on a balloon. You blow air into the balloon. The rubber stretches. The dots move apart from each other. None of the dots are moving across the rubber. The rubber itself is growing. It's a terrible analogy. A balloon has an inside. It has an outside. It expands into the air of the room. The universe doesn't have an outside. There is no room. There is no empty space that the universe is pushing its way into. The universe is all there is. Instead of a balloon, think about a grid of numbers, a coordinate system. You have an object at position 1, another at position 2. The expansion of the universe just means the physical distance defined between coordinate 1 and coordinate 2 gets larger over time. The objects aren't firing thrusters. They aren't moving through space. The metric that dictates distance is fundamentally changing. In the 1920s, Edwin Hubble looked at galaxies. He looked at the light coming from them. Light behaves like a wave. It has a wavelength, the distance between the crests of the wave. If a galaxy is moving away from you, the light waves get stretched out. The crests get pulled further apart. Longer wavelengths of visible light look red. We call it redshift. Hubble noticed that almost every galaxy is redshifted. They're all moving away from us. More importantly, he noticed a pattern. A galaxy twice as far away is moving away twice as fast. A galaxy 3 times as far away is moving away 3 times as fast. That specific pattern only makes mathematical sense if space itself is doing the expanding. Every point is moving away from every other point. For a long time, we thought this expansion would eventually slow down. Gravity pulls things together. All the galaxies are pulling on all the other galaxies. The expansion should act like a baseball thrown straight up into the air. It goes up, but gravity slows it down. Eventually it stops, turns around, and falls back down. A big crunch. In 1998, 2 teams of astronomers went out to measure exactly how much the expansion was slowing down. They looked at exploding stars, type 1a supernova. These specific explosions always happen at the exact same mass. A white dwarf steals gas from a companion star. It eats and eats until it hits exactly 1.4 times the mass of our sun, the Chandrasekhar limit. At that precise weight, the carbon in the cores ignites all at once. The star blows itself apart because they all explode at the same mass. They all have the exact same maximum brightness. They act like standard light bulbs in space. If you know exactly how bright a bulb really is and you measure how dim it looks from Earth, you can calculate exactly how far away it is. The astronomers measured the distance to these distant supernovae. Then they measured the redshift to see how fast they were moving. They found something that made absolutely no sense. The expansion wasn't slowing down. It was speeding up. The baseball wasn't falling back down. It was accelerating up into the sky faster and faster. Something is pushing space apart, that we don't know what it is. We gave it a label. Dark energy. Cut. It's just a placeholder name for our own ignorance. Dark energy makes up about 70% of the total energy density of the universe. It seems to be a property of space itself. The more space you have, the more dark energy you get. As the universe expands, it creates more space. That new space contains more dark energy, which pushes the universe to expand even faster, which creates even more space. It's a runaway feedback loop. This is why the late universe gets so utterly empty. If dark energy stays constant, we get the heat death I described earlier, a slow fade to black. But what if dark energy isn't constant? What if it gets stronger over time? That leads to a scenario called the Big Rip. Right now, dark energy is incredibly weak on small scales. It's only noticeable across massive intergalactic distances. Gravity easily overpowers it within our solar system. The electromagnetic force easily overpowers it within your body. You aren't being ripped apart. But if the density of dark energy increases over time, the outward push gets stronger. Eventually, it gets strong enough to overcome the gravity, holding clusters of galaxies together. The clusters drift apart, and then it gets stronger. It overcomes the gravity, holding individual galaxies together. The Milky Way dissolves. The stars scatter into the void. Then it overpowers the gravity, holding solar systems together. The planets get stripped away from their stars. Then it overpowers the electromagnetic force, the force holding solid objects together. Mountains break apart. Planets shatter into dust. Then it overpowers the strong nuclear force. The atoms themselves are torn violently apart. In the final fraction of a second, the very fabric of space-time is shredded. The math for the Big Rip requires a specific type of phantom energy where the pressure is strictly negative and continually growing. The current observational data doesn't favor it. It leans heavily toward a constant vacuum energy. The slow freeze. Let's think about the slow freeze again, the concept of nothing. What is a vacuum? If I take a glass jar and pump all the air out of it, is it empty? Yeah. No, it's still full of electromagnetic radiation. Light from the room passing through the glass. I put the jar in a perfectly dark box. Is it empty? No. The walls of the box have heat. They radiate infrared photons into the jar. I cool the box down to absolute zero. Impossible, but let's imagine it. Is the jar empty now? No, you still have the virtual particles, the quantum boiling I talked about earlier. You can actually measure the physical force of those virtual particles. It's called the Casimir effect. You take two uncharged metal plates, you put them incredibly close together in a vacuum, just a few nanometers apart. The quantum vacuum is full of virtual photons popping in and out of existence, waves of probability. Outside the plates, you can have waves of any size, any wavelength fits. But inside the tiny gap between the plates, only certain wavelengths fit perfectly. The long waves physically can't exist in that tiny space, because fewer waves can fit inside the gap than outside. The quantum pressure outside is slightly higher than the pressure inside. The vacuum literally pushes the two plates together. You can measure it in a lab. The void pushes objects. This tells us that the empty space at the end of the universe isn't a passive theater where things happen. Space is an active physical substance. It has pressure. It has geometry. It has energy. When the last black hole evaporates, the matter is gone, but the space remains. How do we even know black holes evaporate? We've never seen it happen. We know because of thermodynamics. Jacob Bekenstein was a graduate student in the 1970s. He was annoyed by a logical paradox. The second law of thermodynamics says that the total entropy of a closed system must always increase. Things always get messier. Bekenstein asked a simple question. What happens if I take a box of hot gas, a box with a lot of entropy, and I throw it into a black hole? The box goes past the event horizon. It's gone from the observable universe. We go, did the total entropy of the universe just go down? Did I just destroy entropy by hiding it inside a black hole? If I can do that, the second law of thermodynamics is broken. Physics falls apart. Bekenstein argued that the black hole itself must have entropy. When the box of gas falls in, the black hole's entropy must increase to compensate for the lost entropy of the gas. Where does a black hole store its entropy? It only has three properties: mass, spin, and electric charge. That's it. A black hole has no hair. It has no complex surface features. Bekenstein realized that when you throw mass into a black hole, the event horizon gets physically larger. The surface area increases. He proposed that the entropy of a black hole is exactly proportional to the surface area of its event horizon. Stephen Hawking hated this idea. Hawking knew that if an object has entropy, it must have a temperature. If it has a temperature, it must radiate heat. But by definition, nothing can escape a black hole. It can't radiate, therefore it can't have a temperature. Therefore, Bekenstein must be wrong. Hawking set out to prove Bekenstein wrong using quantum field theory. He ran the math. The math betrayed him. The equations proved that black holes do radiate, the virtual particles at the horizon, the exact mechanism I described earlier. Bekenstein was right. The surface area of the event horizon is a measure of the hidden information inside. This leads to a horrible logical nightmare called the information paradox. Quantum mechanics has a core rule. Information cannot be permanently destroyed. If you burn a book, the information in the book isn't technically gone. The exact position and velocity of every smoke particle, every flash of light, and every piece of ash mathematically encodes the original text. If you had a supercomputer powerful enough, you could reverse the trajectories of all the smoke and ash and reconstruct the book perfectly. The information is scrambled, but it is conserved. Now, throw the book into a black hole. The black hole absorbs the book. Its mass goes up slightly. Then over 10 to the 60 years, the black hole evaporates via Hawking radiation. It spits out random thermal photons. Hawking's original calculation showed that this radiation is perfectly random. It contains absolutely no information about the things that fell in. A black hole made of burned books produces the exact same radiation as a black hole made of pure lead. The black hole shrinks. Eventually it explodes and vanishes. Where did the information about the book go? It's not in the radiation. The black hole is gone now. The information is physically erased from the universe. If information can be erased, probability breaks down. You can't predict the past from the present. The mathematical foundation of quantum mechanics collapses. Physicists argued about this furiously for 40 years. Leonard Susskind got into massive yelling matches with Hawking over it. Eventually, we figured out a loophole, the holographic principle. When the book falls toward the black hole, from the perspective of someone watching from the outside, the book never actually crosses the horizon. Gravity warps time. The closer you get to a massive object, the slower your clock ticks relative to an outside observer. As the book gets closer to the event horizon, its clock slows down asymptotically. From my perspective, watching it through a telescope, the book slows down, stretches out, and smears across the spherical surface of the event horizon. It fades to black, but mathematically the information about the book is plastered on the two-dimensional surface of the hole. The inside of the black hole is a three-dimensional volume, but the information capacity of the black hole is determined entirely by its two-dimensional surface area. All the 3D information is encoded on the 2D boundary, just like a hologram. When the black hole slowly evaporates, the radiation isn't perfectly random after all. It interacts with the smashed, smeared information on the surface. The photons carry the encrypted information of the book back out into the universe. The information isn't lost. It's just mangled beyond practical recovery at hiding. Why does this matter for the end of the universe? Because it tells us that even in the absolute final stages of the dark era, when the universe is nothing but a freezing mist of photons, the history of everything that ever existed is still physically there. The light carries the encrypted scars of dead stars, shattered planets, and evaporated black holes. The total information of the universe is conserved, endlessly stretching out into the dark. Let's look at the dark matter. That we haven't talked about dark matter. If you look at a spiral galaxy like Andromeda, it rotates. The stars near the center orbit fast. The stars at the outer edge should orbit slower, just like planets in our solar system. Mercury orbits the sun incredibly fast. Neptune plods along slowly, and Vera Rubin measured the speed of stars at the edges of galaxies. They weren't moving slowly. They were moving incredibly fast. So fast that the gravity of the visible stars in the galaxy wasn't nearly strong enough to hold on to them. The galaxy should fly apart like a spinning wet tennis ball, throwing off water droplets, but it doesn't fly apart. Something is holding it together. There must be an enormous amount of invisible mass creating extra gravity. We call it dark matter. It completely ignores light. It doesn't absorb it. It doesn't reflect it. It just has mass. It passes straight through solid objects like a ghost. There are dark matter particles flying through your skull right now. It makes up about 85% of the mass in the universe. What happens to dark matter at the end of time? If dark matter is made of particles, weakly interacting massive particles, they might have their own antiparticle. Or they might be their own antiparticle. If two dark matter particles happen to crash into each other, they annihilate. They turn into high energy gamma rays. But space is expanding. The dark matter gets stretched out and diluted. The chances of two particles finding each other to annihilate drop sharply. Most of the dark matter will simply sit there. Invisible dead mass drifting in the dark. If protons decay, the normal matter vanishes. But dark matter isn't made of protons. It doesn't feel the strong nuclear force. It might not decay at all. You could end up with a universe where the only surviving mass is the ghost matter we can't even see right now, invisible clouds of heavy particles drifting in absolute silence. Let's think about silence. Sound is just pressure waves in a medium. Air, water. Space is a vacuum. No sound travels, and but early on, right after the Big Bang, the universe wasn't a vacuum. It was a dense, boiling soup of plasma. It was so thick that sound waves literally bounced around inside it. Gravitational compression heated the plasma up. Radiation pressure pushed it back out. This created massive acoustic oscillation. Gigantic sound waves rippling through the primordial fireball. When the universe expanded and cooled enough for the first stable atoms to form, the plasma cleared. The universe became transparent, but the light flew free. This is the cosmic microwave background, but those giant sound waves froze in place. The areas where the sound waves had compressed the gas became slightly denser regions of space. Gravity took over. Those slightly denser regions pulled in more gas. They eventually formed the vast webs of galaxies we see today. The structure of the entire universe is just a fossilized echo of the sound waves. From the first 300,000 years, the universe started with a deafening roar. It ends in absolute mathematical silence. Let me ask you a question. Why does time only go one way in Alpine? The laws of physics are completely time reversible at the microscopic level. If I show you a video of 2 billiard balls bouncing off each other and I play the video backward, you can't tell the difference. The physics looks perfectly valid. Either way, Newton's laws work equally well forward and backward. But if I show you a video of a glass falling off a table and shattering into 100 pieces and I play it backward, you instantly know it's fake. Glasses don't spontaneously reassemble themselves and jump up onto tables. Why not? The microscopic collisions of the glass molecules against the floor are individually time reversible. The answer is probability, entropy. There is exactly one specific arrangement of atoms that makes an unbroken glass. There are trillions of different random arrangements of atoms that make a pile of shattered glass. When the glass drops, it moves from a state of low probability to a state of high probability. It's simply a matter of statistics. It is overwhelmingly mathematically more likely for things to get messy than for things to get organized. The arrow of time is dictated by entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because our brains rely on increasing entropy to record memories. Creating a memory requires expending energy and generating heat, which increases the entropy of the room. You physically cannot remember the future. So what happens when the universe reaches maximum entropy? When the heat death is complete. When everything is the same temperature. There is no more lower entropy in the past. There is no more higher entropy in the future. The arrow of time disappears. Without an entropy gradient, there is no physical distinction between moving forward in time and moving backward in time. The universe sits in a state of perfectly timeless equilibrium, a sterile, static void where the concepts of past and future lose all physical meaning. But we have to be careful with the word static. Classical physics says the universe stops completely. Quantum physics violently disagreed. Quantum fields never stop vibrating. I talked about vacuum fluctuations. Let's look closer at those. In quantum field theory, you treat the vacuum not as empty space, but as a collection of fields covering everything. An electron field, a photon field, a quark field. A particle is just a localized vibration in one of those fields. When you pluck the electron field, you get an electron. And the uncertainty principle states that a field can never have exactly zero energy. If it had exactly zero energy, you would know its exact value and its exact rate of change perfectly. Heisenberg forbids that. So the fields always vibrate slightly. These vibrations can theoretically cause a completely stable pocket of vacuum to suddenly transition into a lower energy state. Wait, is our vacuum truly at the lowest possible energy state? We used to assume it was, and then we found the Higgs boson, so the Higgs field gives particles their mass. Its energy level dictates the physical constants of the universe. Measurements of the Higgs mass suggest something incredibly dangerous, but our vacuum might not be fully stable, it might be metastable. Think of a ball resting in a small dip halfway down a mountain. The ball is stable. You can nudge it, and it rolls back into the dip. But if you kick it hard enough, it rolls out of the dip and falls all the way down to the bottom of the valley. A much lower energy state, our universe might be sitting in that temporary dip. If a quantum fluctuation randomly kicks a tiny region of space hard enough, that tiny region could collapse into the true vacuum, the valley floor. The laws of physics inside that tiny bubble of true vacuum would be completely different. Electrons might have zero mass, protons might instantly dissolve. The forces of nature would rewrite themselves, and this true vacuum bubble is at a lower energy state, so it expands. It expands outward in all directions at exactly the speed of light. It destroys everything it touches. The fundamental structure of matter gets vaporized and rewritten as the bubble wall washes over it. You would never see it coming. The light warning you of the bubble's approach travels at the same speed as the bubble itself. 1 microsecond, you're standing there. The next microsecond, your atomic structure simply ceases to exist. This is called vacuum decay. It could happen right now. It could have started 1 billion years ago in a distant galaxy, and the destruction sphere is flying toward us at light speed. But space is expanding. If the bubble starts far enough away, the expansion of space will push it away from us faster than it can grow toward us. We might never intersect with it. If the universe experiences vacuum decay, the heat death gets interrupted. The board isn't just rusted away. The board is actively set on fire and replaced with a completely different game with different rules. We have no idea what those rules would be. The math we use to describe reality relies heavily on the specific energy level of the Higgs field. Change the Higgs level, you change the math. I've talked about a lot of highly speculative things, proton decay, Boltzmann brains, and conformal cyclic cosmology, vacuum decay. Let's stick to the absolute rock-solid things we know. We know the stars will die. We know the galaxies will separate. We know the temperature will drop. We know the black holes will evaporate. These aren't guesses. They are direct, unavoidable consequences of the laws of thermodynamics and gravity as we measure them in the laboratory today. Let's trace a single photon of light from our sun right now straight into the end of time. The photon is generated deep in the solar core by nuclear fusion. It bounces around inside the dense plasma of the sun for about 100,000 years. It gets absorbed and re-emitted millions of times. Finally, it hits the surface, the photosphere, and it flies out into space. It takes 8 minutes to reach Earth, but let's say it misses Earth. It misses everything in the solar system. It flies out into the interstellar medium. It leaves the Milky Way. It travels for millions of years. It crosses the void between galaxies. Space is expanding while the photon travels. In fact, the photon's wavelength stretches. It loses energy. Billions of years pass. The galaxies are getting further apart. Trillions of years pass. The stars have all burned out. The photon is still flying. It hasn't hit anything. Space is incredibly empty and getting emptier every second. The photon stretches until its wavelength is the size of a galaxy, then the size of the observable universe. Its energy approaches zero. It will fly endlessly through a frozen, lightless void, uninteracting, completely alone. It will never hit a wall. It will never slow down. It will simply stretch until it becomes functionally identical to the flat line of the vacuum itself. That is the fate of almost all the energy in the universe. It's a bleak picture. People often ask me if it depresses me, working out the math of the ultimate end. It doesn't. There's an odd comfort in the mechanics of it. We exist right now in a very narrow window of time, the stelliferous era, the era of starlight, compared to the endless trillions of years of the dark era. The time when stars shine is just a brief spark right at the beginning of the universe's life. We are living in the explosion. You look up at the night sky and you're seeing the temporary fireworks of a newly born cosmos. The atoms in your body were forged inside the crushing cores of dying stars. The carbon in your DNA, the iron in your blood, the oxygen in your lungs, all of it is stellar ash. You are a temporary, highly complex pocket of low entropy. You are a machine that eats organized energy, uses it to think, and spits out disorganized heat. The very fact that you can observe the universe, that you can measure the redshift of galaxies, that you can calculate the evaporation rate of a black hole, is a miracle of probability. I mean, the universe is slowly breaking down. It is heading toward a state of perfect icy equilibrium, but on the way down, it produced galaxies. It produced stars. It produced planets. It produced chemistry. It produced biology. It produced consciousness. It produced a species of upright apes that looked at the sky and figured out how the whole machine works. The board might eventually rust away into nothing. The game might end in a draw, but the complexity of the moves played along the way is astonishing. We have measured the temperature of the Big Bang. We have weighed the invisible dark matter. We have watched the ripples of gravitational waves from black holes crashing together 1 billion light years away. We figured out the rules. Even if the universe eventually forgets those rules, even if every piece of matter decays into a thin freezing mist of stretched light, it doesn't invalidate the reality of right now. The heat death is inevitable, but it's practically infinitely far away. Right now, the stars are still burning. The galaxies are still spinning. The physics still works. Thank you.